just not just like as applications, just to insight. That means how a manufacturing or design engineer or researcher can connect this area, semiconductor. Because if you generally, when you see this area semiconductor, then the people from electronics and this and the IT, they generally connect. But obviously, for during manufacturing, so we need manufacturing things and some design aspect. So accordingly, I have a plan at least to touch you. So this is a brief. Actually, in this whole session, I have divided this presentation in the how we can connect from this micro aspect and from nano aspect. And in micro aspect, this is the first few slides I will connect from the micro aspect. So in micro machining or micro manufacturing, so these are few of the applications where we can use this micro manufacturing, especially in the last slide. This one is visible. So this is majorly towards the semiconductor application. That means, let's say we have a small chip. So now so for that we need how to dissipate heat to cooling applications. So for this we make some array of micro fins. So, and these are majorly fabricated by micro milling process, and we can say micro machining process. So then when you're thinking about micro machining, then many kind of micro machining processes are there, starting from conventional and non-conventional. Conventional means from where we are using some cutting tool in micron size, around 100 to 500 micron. And some of the non-conventional micro manufacturing process. So among them, majorly this array of pins are made by micro milling, micro EDM, and micro grinding also, and drilling also. So among these processes, obviously every process has its own advantages and some limitations by its own way. Then when we are choosing a process for industrial applications, then few things we have to consider. One is low cost, first thing. Then this process should be versatile. Let's say this feature size is changed, then how we can counteract. Then let's say we need a particular precision, then whether this process can meet that challenge. So by considering all these things, then we see that, okay, this micro milling process is acceptable. But this is not like the conventional milling that we have a milling cutter having, let's say end milling cutter having 5 or 10 mm diameter. So this is, we are using around 180, sometimes 50 micron diameter. So when I'm reducing the diameter, obviously the catastrophic tool failure tool breakage is the major issue. And not like the conventional machine tools we can use for this process. So then, okay, so before that, we should know what is this micro milling process. Then this micro milling actually is a mechanical micro machining process in which machining done by a sub-millimeter, that means around less than 0.5 mm diameter cutting tool. So then what are the similarity and dissimilar, you can say, with respect to conventional milling process? So here you can see this is a conventional milling tool, this is a micro milling tool. If we see just like geometry, you can say, okay, this is very similar, just a scale down version of this end mill. But when you come to its how the chip formation occurs, then it's completely almost different as compared to this conventional milling process, because here the size effect comes into picture. So what is size effect? Actually, those parts I will discuss. So size effect means, let's say in this image, the simple machining process image. So this chip formation occurs by shearing. And but in micro milling process, what happened here, the undeformed chip thickness, means I'm saying the feed per tooth related to this, is very less. But the tool, the cutting tool, what we are making, we can make less than a particular value of this edge radius. We have some constraint in manufacturing. So let's say we made a cutting tool with edge radius. Let's say the cutting tool diameter is around 0.5 mm, around let's say 500, 400 micron. So in this case, the edge radius generally around 2 micron or something. But let's say our undeformed chip thickness value is less than that. So in that case, what happens? Instead of chip formation, there is some flowing and rubbing comes into picture. This is called actually size effect. And especially in case of this micro machining, or we can say micro milling, here the tool rotates and advance in the direction of feet. So here the undeformed chip thickness value varies from 0 then to maximum and to 0. So it passes the zone of flowing, then shearing, and then flowing. So the flowing is inevitable. It will be there. Obviously, we cannot mitigate, we cannot eliminate, but yes, we can mitigate by some means. Then, as a overally, we come to what are the issues in micromilling. What are the overall issue? That issues come from all sides. As a machine tool, when we are doing some machining operations, we have a machine tool. That means, let's say lathe, let's say milling machine, let's say drilling machine, whatever. Some process mechanics, that means how this chip formation occurs. And again, we need a cutting tool. So from all sides, if you will see, let's say from cutting tool, the issue is low stiffness. And in process mechanics, as I discussed, this is the effect of size effect is there. And in machine tool, the effect of run out, vibration, positioning accuracy, and speed, and the speed control. Then how it hampers, what it causes, why we are worried about this. Due to this low stiffness of the cutting tool, it will maybe chatter. Chatter means I'm saying the self-excited vibration, which is in machining, we say chatter. Okay. Then tool can anytime break. This is any catastrophic tool failure occurs, and very rapid tool failure occurs. Then due to process mechanics, high bore formation, surface roughness, then these things are detrimental for a very precision applications. Then due to run out, then due to this machine tool issue, let's say run out, then the chip load is non-homogeneous. If the non-homogeneous chip load means it will obviously some disturbance will come and the vibration will come and damage the inaccuracy come and the tool breakage occurs. The whole, you can say the major two issues are there. One is the quality issue and the cost. Cost means the tool can break. Quality means we need a particular surface quality, or you can say the tolerance and all these things of the features. And how you can counter this challenge? For the cutting tool, okay, we can do some force modeling. That means before doing the machining, we know, okay, this is I will do some model by numerically, by analytically, then I will see, okay, so these are the parameters. On these parameters, I will do my operations, then the tool will sustain. Then stability analysis. That means, okay, I will do some dynamic stability analysis for the chatter. Then, okay, for this is the parameters I will do, then I will avoid this vibration, not vibration actually, this is a self-excited vibration. Then I will use some coated tool, and I may use some kind of lubrication. Then for the process mechanics, okay, so first we'll find for the value of the MUCT, means minimum undeformed chip thickness. Then that if that we can find, then okay, we can avoid this all this thing and modeling of response parameters. Then towards the machine tool issue, we have to choose a high-speed spindle having low runout. And instead of this lead screw, because generally this machine tools are made of lead screw, we will use some hydrostatic ball screw. Then high damping structure. So these are the few approach by which you can control these micromilling issues. In this presentation, actually, I will focus on coating, how we'll do coating and how we can avoid this thing. So obviously, for any research work, when you see, then we see some excellent kind of literature survey. So from this, actually, we obtain the idea how we can proceed and how our work will be different, and how we can enhance the performance of the process. So here, one thing we see that, okay, in general, the idea is there. If we are using some coated tool, means we can enhance the process. But this is not true in case of microwave. So what happened? Some of the researchers, they use some CBN, that is cubic boron nitride coating, which is second highest hardness than diamond. So they see that instead of this decreasing cutting force here, cutting force increasing, then they see, okay, this is due to increase of edge radius. Then another researcher, they see they use three types of coating: nanocrystalline diamond, TIL and TIN. They see that for the TIL and TIN for the titanium grade 5, the significant built-up edge formation observed. Generally, people report that by using some good coating, you can enhance the process. But this process is not enhancing. It is diminishing the performance of the process. So then the next idea came like, okay, we have to choose, maybe this is the relationship between the two matting surfaces, what the tool and what the workpiece. So that we have to investigate. And few other people say that, okay, if we use some solid lubricant kind of coating, then it can enhance. But again, the edge radius is an issue. So those things we have to take care systematically. So here the whole idea was to first to select a particular coating thickness, because edge radius, whatever is there, we cannot do anything, because that is our manufacturing constraint is there. But the coating thickness, somehow we can tune. If you can tune this thing, then obviously we can reduce the friction. That obviously we can get, but we have to mitigate the size effect, which is comes in case of micro scale milling. And next is that maybe, as I told, that from some investigation we see that this not behaving good performance of the coated tool, this may be due to the interaction of the matting surface. Then we have to choose which matting surface we have to choose for which one. Accordingly, this work started. So this is just a few of a micro and mill tool, which these are the edge radius. Okay. So here the edge radius, one thing I just want to clear, the edge radius and we generally study nose radius. These two things are completely different. Nose radius means, the edge radius means the radius of the principal cutting edge. And the nose radius means the point at which the principal and the auxiliary cutting edge meet each other. So that the radius form that is called nose radius. But in micro scale milling, the effect of edge radius is significant. So then we choose the TIL and coating. Then we did coating by, at the 0.5, 1, 2, 3 different coating thickness. Then, so these are the SEM images of the tool and the coating thickness. And also after this, we have to cross check whether what kind of coating we have tried, whether we have obtained this or not. Then that also we confirm. Then after this, the first thing that our application of coating is for the two purposes. One is majorly, one is to enhance the hardness and to enhance the tribological property. That means to reduce the coefficient of friction. So this test we have done for the nano indentation test, that also we see that, okay, for the uncoated tungsten carbide tool, it hardness around 19.2 gigapascal GPa, and for the after TIL and coating, this is around 34.8 or even so 35. This is a huge enhancement of hardness, which is required. Then for the tribology test, what we did here, we choose the TIL and coating and the steel ball. That means the conventional people do this at the counterpart, and we did this tribology test. And here these are the surfaces after tribology test. So here you can see that the coated surface, the uncoated surface, the adhesion is high, and for the uncoated surface, the adhesion is less. So adhesion, these are actually, this is adhered, but the process is a combination of adhesion and adhesion. Adhesion means there is some chemical affinities there, and this material transfer here. And abrasion generally happens, let's say, the hardness of one surface is less, then obviously we generally see the surface is very nascent, that means very clean, but obviously there is some asperities are there. So these asperities are breaks of the less harder surface, and maybe sometime in the more harder surface, and this asperities come in contact between the two meeting surface, and these asperities act as a third body, and that actually progress this abrasion. So due to this, here you can see that for the coated surface, the adhesion is less. So accordingly, obviously, we can get this coefficient of friction of this coated surface, coated surface less. Then our main work started. That means we are okay. First, we confirm that what coating we have done, it has good hardness and less coefficient of friction. Then we have to see then we have to realize the effect of size effect. Then we started experiment in a high-speed micromilling center having 1,20,000 RPM spindle speed. And first we capture the cutting force. So the cutting force we have captured by a mini dynamometer of 𝗕𝗫 at the sampling rate of around 10 kilohertz. And here, so here we can we have done all the experiments for different coating thickness. One is 0.5, one is 1 micron, one is 2 micron, one is 3 micron, one is uncoated. Uncoated means uncoated tungsten carbide too. So in this image, you can see here for the 0.5 and 1 micron coating thickness coated tool outperformed as compared to uncoated tool. And for this 2 micron and 3 micron TLN coated tool could not exhibit better performance as compared to the uncoated tool. So this is due to the size effect. So after this coefficient of this cutting force analysis, we again did the analysis of the surface roughness. Here, similarly, we see that for the coated tool having 0.5 and 1 micron coating thickness, it showed the better result as compared to uncoated tool. And for the 2 and 3 micron coated tool, it could not outperform. And the bore height is also a similar result. Here I can just clear what is bore. Bore means, let's say we are making a slot. So generally our chip formation occurs by shearing. That means the whole material should be formed as a chip. But in micro milling, as I told, that the effect of size effect is there. That means there's some flowing concept. Flowing means just like when you when are doing some digging, just like by some in a field. So by, let's say, by a tractor. So this soil, we are not just bringing it out. We are just giving a side motion. So similarly, some materials did not come out completely. It sticks on the side wall. This is called flowing, and this the sticked material we are saying this is as the bars. And but another thing we are very curious. So in general, what happens? Okay, so at a 2 and 3 micron coated tool, you can say the size effect is due to the higher coating thickness. That means the least force and least surface roughness and least bore height should come for 0.5 micron coating thickness. But what happened here for the fresh tool, that is after the first pass, the results are very clear. For the 0.5 micron coated tool, this is showing better result. But here, after long pass, for each pass we have taken 30 mm machining length. So we did around 40 passes. Then after that we see that instead of 0.5 micron coated tool, this 1 micron coated tool outperformed. Then we see that why these things are happening. Then we analyze the edge radius of the own tool. So when you see the edge radius of the wound tool, then we see that the least edge radius after a long machining length is for 1 micron coating. From this we clear, okay, for the 2 and 3 micron, due to higher coating thickness, the effect of size effect is there. And for very less coating thickness also, what happens? This coating is not sustaining. So therefore, once the coating came out, or you can say there's just delaminated, then this tungsten carbide come out outside. Then obviously the more friction and more plastic deformation, everything can happen. So from here we can say that this 1 micron, the coated tool having 1 micron coating thickness is showing the best result. So from here, first thing we concluded that, okay, so among different coating thickness for this micro milling, if we want to use a coating thickness, so we need a trade-off. Means we have to avoid the size effect. Again, we have to keep the coating intact. For this, we have to choose a coated tool of coating thickness having thickness around 1 micron. Then after this, the next part started. So next part means, as you see, as I told that in general, the researchers reports that just use a harder coating, you will get a better results. But this is, as I told, that this is not always true. Few researchers, they reported that no, this is not true. But that could not reveal why these things are happening. But they told that these things are happening. So this gives a clue that okay, let's do some research work that we may find some insights. So then what do we think? First, we intuce that this may be due to the effect of the matting surface, maybe cohesion, maybe adhesion. So then to check this thing, then what we did, so okay, so these are the frontline coating material. One is TiLN and TiN. These all are the ceramics kind of coating material. One is metal, one is non-metal, and the TiLN is nowadays one of the front leading coating material. Then a comparatively new coating material is coming, that is called DLC, diamond-like carbon. Actually, this is a amorphous structure of carbon. Actually, some kind of, it can the structure some kind diamond, sometime kind of graphite. That means sometimes sp2 is more, sometimes sp3 is more. So then according to our use, we choose which kind of combination we will choose. Then so the coating thickness part is fixed, that means 1 micron, but obviously, during coating, we cannot do exactly 1 micron. So here our coating thicknesses are around 1.1, 1.06, 1.2. So that means we can say average, we can say this is 1 micron. Then we coat 3 kind of coating. One is TiLN, one is TiN, one is DLC. This DLC is diamond-like carbon. And obviously, after that we have to cross-check whether this is TiLN or not. This is TiLN, this is TiN. Then in carbon, actually, this is a combination of carbon and hydrogen. So hydrogen we cannot see in this index. So that's the only carbon is there, and few dopant is there. This because we are using incandescent atmosphere, so argon somehow comes. Next, our aim is to then how we'll choose, because few people are saying the TiLN coating is one of the very good material. Few people are saying we use TiLN and our flip force is more, the built-up edge is more, roughness is more. Then we thought, okay, so then we have to do. So we choose 2 material, 2 frontline material. One is Ti6Al4b, that is grade 5 for the aerospace grade. So here the combination is titanium and aluminum and nitrogen also. Sorry, vanadium also. And next is we choose P20 steel. So that is one is ferrous material, one is non-ferrous material. So we started doing this kind of thing. Then after coating, we did some nano indentation test, and here you can see that the maximum penetration occurs in case of uncoated tool because the hardness is least, and the hardness maximum came in case of TiLN coating, and next TiN, and then next is DLC coating. Then for the coefficient of friction test, that we did carefully. So for one test, we use this P20 steel as a counter surface. For another one, we use this Ti6L for what exactly we are using. That means both this counter surface, the pins, we used what exactly we want to machine. Then we can find the inside. That was the whole purpose. So when we see that we use the steel surface, so just as a conventionally, what people generally say that we receive that for the uncoated surface, the coefficient of friction is maximum, and the minimum is for the DLC and less for the TIL and TIN. So this TIL and TIN less because there's less hardness. If it, sorry, more hardness. If more hardness, then more abrasion resistance. If more abrasion resistance, then more third body friction things. And DLC is least because it is in more sp2 form. That means more solid lubricant form. That graphite is graphite form. That's why the least coefficient of friction we received. And in case where we used Ti6L4V as a counter surface, so this result actually is so interesting here. That means here we see the coefficient of friction is more in case of TILN and TIN as compared to uncoated tool, which is this is the first time actually that we reported that time. And obviously least is for the DLC coated. Then we check the wear track of this after the coefficient friction test. This is the wear tracks of the uncoated TILN, TIN, and DLC coated when we have used steel pin. So in this case here, you can see the more adhesion is there in case of uncoated tool and less as in case of TIN, and only one image we have shown. Okay, TIN, DLC, and TILN. So this is obviously due to this both abrasion and adhesion is more significant in case of uncoated tool because the hardness is less. And next, this is the wear track of this after the coefficient friction sample when we have used the Ti6L4V at the counter pin. So in this case, we can see here, as compared to this uncoated sample, here the adhesion of this aluminum and titanium is very significant as compared to this uncoated sample. So that are the reason actually, because the titanium and aluminum are there in both sides from both the matting surface, one workpiece side and the tool side. So similarly, you can say one is for the pin side and you can say the plate side. So therefore, the similar material they easily transfer from one surface to another surface. So this results came. Okay. So then after we check the tool wear performances by doing some micromilling test. Similarly, we did the test for 40 passes. So one pass is 30 mm. So 40 passes we did, and we can see here. For the uncoated tool, obviously, the uncoated tool, the hardness is less. So you can see that the plastic deformation chipping is very significant. And in the TILN and TIN, this is also higher tool wear is there. And in DLC coated, so the tool wear is less. But another thing also here we see that the adhesion of this coating, that in the adhesion strength is not that much very good in case of TLC. So that the future research work we may work or we may work. So here you can see that the flank wear is significant for uncoated tool and the tool wear is minimal for DLC coated tool because the DLC coated tool is a combination of the graphite and the DLC or the diamond properties, the sp2 and sp3 properties are there. So next, here you can see that for the micromilling of Ti6L4V, that means here we did machining of this grade 5 titanium alloy. So here that result you can see the adhesion of that means kind of the built-up edge is very significant in case of this TILN and TIN coated tool because the similar results we have obtained during when we investigated this coefficient of friction tracks of this wave tracks. And the least tool wear has happened for the 𝗕𝗪𝐶 coated tool, but still there is some delamination is there. But the plastic deformation kind of things are very significant in case of this uncoated tool, and the edge rounding also very strong edge rounding of the higher edge rounding we see here for uncoated tool. So here we can see the fracture of the flank face is observed maximum in case of uncoated tool, and the built-up edge formation is significant in case of 𝗕𝗏 and 𝗕𝗏𝗏 coated tool. That means here what is happening actually, these tools are strong, but the built-up edge is forming, and after a particular time this built-up edge chipping occurs. When the chipping occurs, it carry away some material. That's why some kind of chipping here we observed, and again that is giving rise to higher. Then obviously here we're comparing machining of both the material. One is P20 steel, one is Ti6L4B, and all this experiment done for all the same kind of coated. One is for the uncoated TILN, TIN, and DLC. Similarly, TILN, TIN, and DLC uncoated tool, and one is P20 steel workpiece material, and one is Ti6L4 with the titanium grade 5 alloy, aerospace grade alloy. So this is the one machining material. So here you can see that for the own tool, the least edge radius was obtained for the TILN coated tool, but for the titanium alloy Ti6L4 machining, the least edge radius obtained for the DLC coated tool. And similarly, the cutting force for the P20 steel is minimal in case of TILN coated tool, and all the coated tool outperform as compared to the uncoated tool. However, in case of Ti6L4B machining, this TILN and TIN coated tool could not exhibited better performance as compared to the uncoated tool. However, the DLC coated tool exhibited the best performance. And these are the SEM images of this micro milling slots obtained for both for the P20 steel and for the Ti6L4B, and we used all kind of the similar kind of coated tool, the coated uncoated tool. This is uncoated tool, and this is TILN, TIN, and DLC coated tool. So here the similar results we can see here that for the machining of P20 steel, all coated tool exhibited better performance, and the best performance exhibited by in case of bore height. This is for the DLC. However, for machining of Ti6L4B, this TILN and TIN could not exhibit better performance compared to uncoated and DLC coated. So this is the 3D topography of this surface roughness of the channel, of the bottom channel actually. So this image in generally, this you can see here, we have written SA. Generally people write RA. RA means if you are scanning for a line, but here we scan this area. When the aerial surface roughness things come, then this aerial, then this SA things. And here we have taken the data for SA and SQ, and this is the one sample data, but for the result will show that it is a average of the 5 tests. Otherwise, we cannot say which one is better, which is not good. So similar to this other results, here the TILN coated tool outperformed as compared to uncoated tool for the machine for the micro milling of the P20 steel, and for the micro milling of titanium alloy, this TILN and TIN show the better performance as compared to uncoated one, and but the DLC coated continue. That means just sustain this machining performance and exhibited the best performance. So overall, if you can see here, for the resultant cutting force, surface roughness, and bore height, here you can say for machining of P20 steel, for the all the coated tool outperformed this uncoated tool. However, for machining of titanium alloy, Here you can see the 𝗕𝗏 and 𝗕𝗏𝗛 coated tool could not perform, could not exhibit better performance compared to uncoated tool. So from here, the reason is that you can say and almost in all cases, the DLC has the least force, roughness, and bore height value. This is due to the least coefficient of friction value. And after 120, 1200 mm machining length, as I shown there, there's some delamination occurs for this DLC coated tool. Therefore, the 𝗕𝗏𝗛 coated tool exhibited the better performance. And for the machining of 𝗕𝗏𝗃𝗃4b, the DLC exhibited. So here, one thing is very clear. That means we should convey this message that if we want to machine or micro machine or whatever, the titanium alloy, then although the 𝗕𝗏𝗛 and 𝗕𝗏𝗛 are now at the front line coating material, we can't use because the more adhesion will occur. So either if you will see about the cost aspect, we can use uncoated one, or we can use a coated tool whose constituents should not fall under the category of titanium, aluminum, or vanadium. This is the whole takeaway from these investigations. And this is the whole summary. The appropriate coating thickness is obviously for the micro milling, the appropriate coating thickness we need to take around 1 micron. And for the DLC coated, outperform for all kind of machining, but for the especially for machining of titanium alloy, we should avoid this titanium and aluminum composition having some coating having titanium and aluminum components. So this is all about the micro machining part. That means how we will relate this micro milling with this semiconductor applications, majorly on the chip applications. Actually, you have seen in the chip there is some array of pins. You know, very obviously, if the area increases, then the heat transfer increases, the whole thing. Because any research work, this is related by some thematic. That means, although this will be used in some semiconductor, but you have to manufacture. Then how we have to manufacture? Let's say this is the process, but by doing this thing, then you have to cross many issues. That means you have to take care of these issues to reach. That means, okay, how easily we can do. So on the next thematic thing is that, as I told in this work, so 2 things we will cover. One is micro aspect that already we covered. That means we see that this micro array of pins we can made by this micro milling process. And the tools which are using, this is diameter is around 100 or 200 micron. You can serve them. And 100 micron means I'm saying which is diameter of your hair. Okay. So, and sometime less than that, sometime, because we have used the micro milling tool having diameter around 80, 70 micron. Less than that till now, we have not manufactured. Manufacture means it is not sustaining for the machining. Okay. So during operation, you know, if the diameter is the diameter just for your diameter of your hair, then it can break anytime. And we have to make array of pins. Array of pins means, let's say, we have to make pins having 20 by 20 pins. So that is, and if one tool break, then the whole process is we have to start it again, because we cannot insert another tool and we can start, because the whole program is one program, and we cannot do by doing some part programming. That is again one of the issues. Okay, so the next part of this presentation or the discussion, you can say, I am considering the discussion, is that aspect of this nano engineered surface for the semiconductor applications. So when we are saying this nano scale surface, or you can say nano engineered surface, then obviously it has many applications, like precision optics. Let's say we need some mirrors, because now we are using, these are the mirrors. So let's say we want to use the mirrors for the telescope. So for that, we need a lightweight. We cannot use this what generally we use in our house homemade applications, like some glass, because it can break anytime. So let's say one telescope we are using, and maybe in one mirror we are using in our satellite. So we want a mirror which can sustain. It cannot break by any jerk, against any impact, or it should not be, and it should not be much corresponding to temperature, humidity. So therefore nowadays people are using, that means now we are using metallic mirrors. That's a new area they are using. So for let's see, we want to use in a metal as a mirror. That means we need to make it finish at least less than 10 nanometer. Then only we can use. Similarly, in microelectronics and MEMS applications, we are using silicon wafers. Silicon wafers for some sensors and some many micro devices, and many applications are there. And these are majorly of silicon, either monocrystalline silicon or maybe polycrystalline silicon, with respect to applications we are using. So majorly we are using this monocrystalline silicon for these wafers for the semiconductor. That means in this microelectronics and MEMS applications, obviously it's made up of semiconductor. So then how we will make it super finish? Super finish means we have to finish this to a level of less than at least less than 50 nanometer, sometime 10 nanometer, and some people are giving result in angstrom level, in the surface toughness in angstrom, not in micrometer, not in nanometer, in angstrom. Then how we'll do? And sometimes what happened, for a few applications, we need some free-form surface. Free-form means not flat, it has some form. So how we'll polish? And that polishing also we need in nanometric level. So these are the few challenges that have to take care. So these are very few new kind of things started people doing research. So we'll go step by step why we'll do a particular process and what are the limitations and how we'll achieve. So when the word finishing, when this word finishing comes, then the first term comes into our mind is grinding, because this is kind of a machining, not exactly machining process, because here the material removal rate is very less. So we are using grinding, but the grinding thing is that this is a very rigid tool. You know, there is some wheel, the grinding wheels are there, these are very rigid. So for any complex surface, we cannot do machining. And by grinding, getting nanometric surface toughness is kind of not possible, challenging, not possible. So next process came, that is called honing. In honing, what exactly we are doing? We are finishing the internal surfaces. Honing means, let's say we have a just like a shaft. On the shaft periphery, we are mounting some clothes. Clothes means some abrasive clothes. So that is polishing one drilled hole. But still, we cannot do finishing of nanometric scale. The next process came just like lapping. Lapping means there's some abrasive, there's some slurry, and you are giving some motion of a zigzag, means majorly, and by 8 kind of motion, and you are getting the results. So every process have some limitations. So then some advanced finishing process came. One is called magnetorheological finishing. That means here you are using some rheological fluid. Let's say this is one ball kind of shape, let's say one orthopedic implants. Let's say you need to polish your hip joint. There is some ball and socket. So ball need to be very highly finished. If highly finished means less friction. Less friction means this the prosthesis is highly durable. So for that, let's say this process started for this magnetorheological finish. For you are using some magnetorheological fluid, that means which is responsive to magnetic field. Where you so on the fluid we are using some magnetic material like carbonyl iron particles, and we are using some abrasive. So when applying some magnetic field, then this rheological fluid, now it comes to solid state. The stiffness increases. So then by that we are doing some finishing. So next process is that diamond turning. This is we are using by a single crystal diamond. But the issue is that this whole setup is very costly. Minimum 3 to 4, minimum 4 crore need for a small tabletop diamond turning lathe. And as that we are using some conventional tools, so obviously feed mark will be there. That we cannot avoid. Maybe you can minimize, but it will be there. Next process came, that is called abrasive flow finishing. Means, let's say we want to finish some internal channels. So then in this process, what happened? By some fixer, we fix this, let's say that workpiece, that job, which internal channels we need to finish. And in the chamber, we are adding some abrasive fluid. That means maybe abrasive fluid, abrasive word coming means the first term come like silicon carbide or maybe aluminum oxide. So these all are ceramics material. So this in a slurry we are keeping here, and from both sides we are giving some hydraulic press and giving some to and fro motion by this. Okay, so this can be one way, maybe two way, maybe other elements. So this is a two-way process I have shown here. So by this we are finishing the internal surfaces of the internal, so the surface of the internal channels. So after that, let's say let's say we want to finish on free-form surface. Free-form means, as you can see, this is the surface not flat. This is just like some free-form. Okay. So one process developed in Japan. So this is called shape adaptive grinding. All this is not very old. This is a comparatively newer process. So what they did, instead of a rigid grinding wheel, they use some elastic material, rubber here. If you can use a rubber, so then it can take the shape of the free-form surface. So it should be very clear. One thing I want to clear that. So I'm saying free-form surface. I'm not saying complex surface. So complex geometry is something different. And the free-form means the form is not flat. This is free. That is some wavy things are there. So there is elastic tool material, and outside of this tool material is they're just covered by some abrasive pad. Pad means just like some abrasive clothes or abrasive, we can say, paper are coming. So by that they are doing this policy. This name is shape adaptive grinding. So here what are the advantages here? That is, obviously it can conform to complex and intricate shape and ensuring uniform material removal. That is one of the major part. Otherwise it can make lots of scratches. Then precision, obviously we are getting nanoscale surface finishes, and versatility applicable across all kinds of material. All kinds of materials here I'm saying means some metallic materials are soft. So those who have experienced this thing, they know. Let's say I have a copper. Copper by grinding, let's say by hand grinding also, I can polish it very for up to a particular surface toughness. I can easily remove material. But to bringing it to nanometric level is not easy. That is the challenge. Because there's soft material, so easily it can scratch. So the scratch marks increases the surface roughness. So then, although it is soft, again it has a challenge. So next we thought that here the another challenges is that, let's say that abrasive pad or the abrasive pad what we have wrapped on the periphery of this elastic tool, after few time this abrasives are wear out on the pad, and the workpiece size is not very small, it has some particular size. Then the life of that thing is over. We cannot reuse, because again you have to start from the scratch, not from that process where ends. We cannot start, because we have to change that abrasive pad. So we thought that just like grinding, if we can make one self-replenishing nature of a grinding wheel, and it should be soft, can we make this thing? Then that the whole thing we started. This is not exactly the mature stage, that also we are struggling in many ways. For this, actually, we take the help of this material chemistry. So now we have to use the abrasive as a silicon carbide or aluminum oxide, and the matrix which we want to use, that we want to use just like a PU, polyurethane. But we cannot embed it on the outer surface. We have to make a solution. So for the polyurethane, we found that, so there are the two materials there. One is called tetrahydrofuran and one is dimethylfuramide. So these are universal solvents. So if we make solution in a hot plate, we can make 100% of solution. And once the PU is solution we made, then obviously we can put this abrasive, this silicon carbide as abrasive. Then we stir it homogeneously. This is the whole aim that we started. And this is the SCM, obviously, before doing this, let's say from one company we are getting the materials, he's saying it is of 9 micron size. But when we are getting this abrasive by some ball mill, all shapes are not same. But at least we try to see if they are saying this is 9 micron, whether it is obeying this normal distribution curve or not. That means the majority of this abrasive should be fall in 9 micron size. So that actually comes. Yes. Then we can say average size is 9 micron. That we first test. Then after making this solution, we have some we made some die, or we can say, sorry, mold. Mold should have a shape of this one abrasive wheel. So that we pour onto that mold and we allow to evaporate, because we have added this solvent. So solvent need to evaporate and we have to dry. And all this we have to do in a controlled environment. So for this, we use this desiccator. Then here we use different concentration. One is 3%, one is 5%, one is 7%, this is 10%. We don't know which concentration will work better for us. So we just name this thing, 3% is S3, 5% is S5, 7% is S7, and 10% is S10. Then this is the tool. You can see just like after this solution and by drying we obtain, this is an elastic abrasive tool. And to this tool, actually, we did the SCM analysis. We have to see that how the morphology of this tool. Then we see that for the S3 tool, the abrasive percentage is less. So here, this abrasive are not much protruded out. This is covered by the matrix material in the PU material. But for the S5, S7, and S10 tool, here we see that these abrasives are homogeneously protrude out. Then we did some IREX analysis that we have to see that what kind of material we have used that is there or not. That is the first step. Otherwise, after doing all the experiments, results will not come and we'll see why it's coming. That means every steps you have to cross check. That is done. Next, here what we did, as I told, this process started in Japan. And in world, one company is there that is called 𝗕𝗂𝗃. He is supplying only this polishing machine. So we see that initially we can afford the price. So we thought that, okay, we are the engineers, not only researchers or not only professors. So we can just, we can make a machine to by our own. Then we just change a tabletop CNC and milling machine to a polishing machine by changing all kind of fixtures from the tool side, from the workpiece side and all. And this is our whole fixture from where we did this experiment. And this is just the property, because here we have, as I told, for the mirror and this kind of, okay, this is actually a case study I am showing. That means how we did polishing. Although we have not started polishing for this is the polishing for the silicon wafer. This is for the polishing of the 𝗕𝗵𝘂𝗃𝗃 copper, because in telescope applications majorly, now we are coating, let's say, nickel. So nickel should have a base, and the base weight should be less. And we see that the 𝗕𝗵𝘂𝗃 copper, oxygen-free high conductivity copper, less density. If less density means obviously less weight. And this is not corroded much. And it can easily adhere to that nickel or something glazing material. And you know, any coating, what the substrate roughness that will be copied on the texture of the coating. So that means before that we have to make it nano-finished. So that part we started. This is actually ISRO given problem. Then for this we use, this is our finishing parameter, like 1000 RPM, spindle speed, depth, not actually depth of cut, this is the depth of penetration, 1.5 mm, and initially we use 3 feet. One is 50, 100, 150 mm per minute, and we did all experiments for 3%, 5%, 7%, and 10% concentration. So these are the results, the surface roughness results. Before polishing, we did some grinding of this cup. So that we obtained the roughness around 132 nanometer. So we need less than 50 nanometer. For that, we started this experiment. This is for the S3 concentration tool, which we did finishing at 3 different feet, 50, 100, and 150 mm per minute. So here for the S3 tool, we see that we obtained the least roughness is around 41 nanometer. And for the S5 tool, we received around 15 nanometer, 15 nanometer. And for the S7 tool, this is around 18 nanometer. And for S10 tool, this is around 29 nanometer. So here you can see the initial trial, we obtained the roughness around 15, and this is average roughness. In some places, obviously, on the periphery may be higher, and the center it may be somewhat so periphery least, and in the center somewhat higher, because this is the action of the centrifugal forces. And another thing we see that with increasing feet, the roughness value decreases in all cases for S3, S5, S7, S10. But in generally, as a machining person or finishing person, we know when we increase the feed, then roughness value increases, but here it decreases. So this is another interesting result. Okay? So that reason is that here we are not removing material in a macro scale. Here we are removing material micro and nano scale. When this removing material micro nano scale, as in the previous in the micro milling slides I have shown, an effect of plowing comes into picture. This plowing word we never know during any machining research. So in that case, in micro scale, this plowing is coming and the burr is forming. So if we're removing in nano scale, then obviously the plowing will be more significant. That means if we are reducing for the less undeformed chip thickness, higher plowing. And the undeformed chip thickness is related to our feed. So the more feed means more undeformed chip thickness. If more undeformed chip thickness means we are decreasing the chances of plowing. If we are decreasing the effect of plowing, then obviously surface roughness will be better and better. So therefore, we obtain better surface roughness in case of higher feed. And this is the overall result. That means here you can see with increasing feed, these roughnesses are decreasing. And the least roughness we obtain for S3 and S5 tool. And in terms of percentage also we can say, so at the 150 mm per minute feed, the roughness is least and the reduction obviously will be high. From here, two things we see that we have to keep, obviously more research required to optimize this roughness, the roughness value. So more feet will try, but now this is the result. And the concentration, that we have to keep the mediocre level, maybe 3%, sorry, maybe 5 or 7%, which is giving better result. And this is, you can say here, as I told, so mirror, you can say, see here. This is the result of a 15 nanometer. This is the initial S5 tool before polishing. The roughness 137 nanometers, so there is no mirror effect. But after the 150, after a particular passes at a feed of 150 mm per minute, it just looks like a mirror. Whatever the paper you have shown here, this is complete mirror, but still there is some corrosion is there that we have to take care. And okay, so after this, as I told, here the corrosion things are coming. So then we have to take care. Okay, so as I told that, and the center, these things came more. So then we thought that how we will take care of this thing. Either we have to use some lubricant. And next is that we have to mitigate the third body abrasive. That means whatever the material is removed from the workpiece surface, those materials should be accommodated on this abrasive tool, just like our grinding. You know, in grinding, there is some porous structure is there. If you'll see in a high resolution microscope, you can see this grinding also looks very hard and rigid. Still, that is true, but the structure is porous. Then the next aim is that we obtain our flexible abrasive tool. That means you can say a flexible grinding wheel that we obtain. The next aim is that we want to make it porous. So again, similarly, we again take this help of this chemistry. That means how we can make this porous. Okay, we can do by salt leaching. By that we can make porous. That means the initial steps are okay. Casting is done. After casting, the salt leaching, and this is the normal table salt we used. Salt leaching we did. By that, some material removed, and here you can see this is a porous abrasive tool we obtain. And this is a normal flexible abrasive tool. So this same flexible abrasive tool, we made it porous here. After this, then we see what the effect of lubricant and what the result in its dry condition and the effect of porosity. So all this, some work is done. So this is a normal elastic abrasive tool, and this is a solid tool. Then if we see under one ideal microscope by SEM, we have seen that the porous structure are very clear, prominent here. So next, we see how this tool are absorbing fluid, because if you absorb the fluid more, then it can take away the heat. If it can take away the heat, then effect of this burning effect, not exactly corrosion, here the burning effect we can mitigate. So you can see the fluid absorption capacity is significantly increased in case of salt is too, because there is porosity. That means this fluid accommodated on the space made by this porous structure. Then okay, here we have not done more passes, just one passes. We see that for the salt is tool, the roughness value we're getting better result. And here in a quantitatively, you can see here, when you have used salt leach tool and DI water, in that case, after first pass, if you will do many passes, then obviously we can get here roughness around 1 or 2 nanometers. Just have seen how it is decreasing. This is around significantly decreases for the salt leach tool and where we have used the DI water. So from here, okay, from here actually we see that we can make a flexible grinding wheel, which can, and it has some, first point was we need a tool having self-replenishing nature, that we obtain. Next, that we need some porous structure, that we obtain, and for the result I have shown here, this is the initial, some early stage, so with time more results we'll get. So from the overall discussion, here you can see that we discuss about how we relate this micro machining and nano scale finishing, that you can say the super finishing. So there is some difference of this finishing and super. That means in finishing, we are restricting ourselves in micrometric level surface roughness. But in nanometric finishing, we're coming up to 1, 2, now the next aim is we have to go to the angstrom scale surface finishing. If the surface finish will be high, then heat dissipation will be high. If heat dissipation will be again high, then the performance of the chips will be more high. So, okay, thank you for listening me here. And thank you, Dr. Sushri Ipshita and Dr. Kshitij Das for inviting me for the session. And thank you all the participants to be here to listen this state-of-the-art some research work. And if you have any query, you are feel free to ask me now.
Excellent session, sir.
Sir, you spoke about milling. Hello.
Yes.
Sir, you spoke about milling. Sir, the tool was cylindrical or it is rectangular?
No.
In milling?
This is end milling. This is
End
end
milling.
milling. So end milling
Okay.
means the tool is obviously cylindrical tool, but obviously on the fluid section, there is some geometry is there.
Okay, sir. Okay. Thank you, sir.
Okay, thank you.
Excellent session, sir. So truly inspiring.
Thank you.
So
Thank you so
anybody-
much.
Please, if you have any questions, dear participants, please ask. Hello, please. Please ask if you have any queries.
Hello. Hello.
Hello. Hello. Hello,
Ma'am.
ma'am.
Can I ask a question?
Sure,
Yes,
sure.
ma'am, sure.
Okay, sir. Sir, what type of sensors and techniques actually monitor micro milling process in real time?
Yes. So real time actually, we are using, let's say, real time monitoring means we are concerned about the tool failure. So tool failure for that actually, generally people use a few sensors like force sensors by using some dynamometer and some vibration sensor by using some accelerometer and some acoustic signal. So among these, and sometimes is acoustic signal, and but among these, if we will consider for the monitoring, if we will take the data, you are using, let's say how much force is there, you can use force sensor. But for the monitoring, majorly people are using this vibration sensor, accelerometer, because two things are there. To processing the data is more faster, and what kind of frequency range this data are coming. That means obviously for
Okay.
any monitoring, you have to analyze in frequency domain, not in time domain. So for this, better you can use this vibration data.
Okay. Sir. Thank you so much, sir.
Thank you.
Any other questions? Any other questions by participants?
Hello. Hello, sir.
Yes, 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 please, you can.
Hello.
Yes, yes.
Sir, can we use the application of micro milling in microfluids?
Yes, yes, because those people are working in microfluids. Means I'm saying, let's say people in a different way. Let's say some people are using microfluids, means the enzymatic analysis, how to divide these enzymes and all. For their need for these microchannels, you know, there is some shape that is you will enter this microfluid one channel and is some party dividing many channels. That is some applications. So for the micro channels,
Okay, sir.
preparation in microfluidics people are using.
Hello.
Okay, sir.
Okay.
Thank you.
Hello. Any questions? Any other questions, please? Okay. Thank you, sir, for your insightful and engaging talk. We truly appreciate the time and effort you have taken to be with us today and share your knowledge. On behalf of both of us, Dr. 𝗕𝗫𝗪𝗛 and myself, and behalf of all participants, we extend our sincere gratitude to you. Thank you so much, sir. The talk was really excellent. Thank you
Thank you
so
so
much, sir.
much. And obviously, as I was very happy because I see some. Initially, I don't know now people are there because I know Dr. Das. Actually, he is one of my senior colleague during my
Yes,
starting
sir.
of my career, and few participants are there. Few are, I think, my teachers also. So
Wow.
it's my. I am very happy that in front of them that actually I started learning from them. And I see, I could not see all the participants, but at least I see Professor Pradeep Jaina was there and Professor 𝗕𝗫𝗃𝗃 was there. These are my teachers because from them
Wow.
actually I have learned a lot. And they are initially, well, obviously, during starting of my career, also few people saved my future. So thank you. If they are here, so I want to thank you, thankful to them.
Thank you. Thank you so much, sir. Okay, sir. Thank you so much.
Okay, thank you.
Okay. Hello. Angapane, sir. Sir, are you there?
Can you hear me?
Yes, sir. Yes, sir.
My voice
Yes, sir.
clear,
We can
right?
hear you.
Yeah.
Yes, sir.
Yeah.
Okay. Thank you, sir, for joining. So for session 6, we have Dr. Subramanian Angapane, sir, who is a scientist at the Center for Nano and Soft Matter Sciences, CENS, Bengaluru. He earned his PhD in physics from IIT Madras and postdoctoral fellowship from JNCSR. He has worked on nanomagnetic materials in South Korea before joining CNS. His research interests include metal oxide based nanomaterials for multifunctional applications such as gas sensors, resistive switching devices, photodetectors, light trapping, solar cells, and magnetic memories. He has published over 77 peer reviewed papers in international journals, and he has guided 6 students till now for PhD degree. And recently, Dr. Angapane received the silver medal from Chirantan Rasayan Sanstha, CRS. We are truly honored to have you, sir. Thank you so much, sir. So please share your screen.
Thank you for the kind introduction. Can you see my screen?
Yes, sir. Yes, sir.
Maybe I'll do one thing. I'll go to full screen and share that. Is it full screen now?
Yes, sir. It's full screen.
Yeah. Thank you. Thanks to the organizer for this kind invitation to present in this faculty development program. This is
The
one of
honor
the.
is ours.
Thank you. This is one of the interesting programs. Actually, I appreciate this program. This is maybe like several of the presentation I made in this. So essentially, this helps the teaching community, those lecturers in the college, teaching in college, to get the idea about the current research. Okay?
Yes,
so
sir.
that will in turn help them to motivate the students. Okay, so
Yes.
like what I am going to present is like covering some basics of these topics as well as like what is current work which I am doing in this topic. Okay, so before going to the details of my talk, I would like to briefly tell you about my center. Our center is called Center for Nano and Soft Matter Sciences. This is the autonomous institute under Department of Science and Technology. This center, like we are situated towards the west side of Bengaluru, and this center is like kind of like about 30 years old. So this is established by one of the well-known liquid crystal scientist, Professor 𝗕𝗫𝗙𝗪. Okay. Later, like kind of this has undergone different changes, and Department of Science and Technology took over the institute and broadened the scope of research. Then the nano was taken into it, and it becomes Center for Nano and Soft Matter Sciences, which is now. Okay, we are kind of situated in a kind of a lush garden like campus, about 17 acres, and we have like kind of limited building as of now, but we are keep expanding. Okay, so we are kind of about 10 faculty and about like 60 PhD students so far. And apart from that, we have a lot of projects running. So our institute is basically academic research institution. Apart from the academic research, we also do some sponsored research for industries. So we have kind of projects from the government agencies as well as the industrial. Okay, so there are a lot of R&D assistants working in our center and postdoctoral fellows, and like kind of we have a state-of-art laboratory facility, kind of we call it a central research facility, which is open to all like throughout the day, like 24/7. That lab is open. The students can work anytime in the day. These are all the important features of our center. Okay, with this small introduction, I will move to topic of my talk today. So today I'm going to talk about the gas sensors. Okay, as you can see, the gas sensors are like very important for this for environmental purpose, like the as well as the medical reasons. If you see this, like wow, what is that major emission of gases coming from? This about 60% is coming from the industries, like any production industry and power plants and the transportations. Okay, what is the main gases which is present in this industrial emissions? That is CO, NO, SO. We call COX and COX, NOx, and SOx. Okay, and ammonia gases. So our interest in this field is now like to develop sensors to monitor these gases emitted from these various industries, as well as for like how this is like this gas emission, gas sensor can be applied to the medical field. Those are all the two aspects which we are trying to answer. Okay, so if you see this slide, like what is the effect, effect of these gases on the environment? So like as it says that environmental wise, it is having effect of producing acid rains. It inhibits the plant growth and it damages the ecosystems, and the ozone layer thinning. The thinning is happening, and also photochemical smog is happening because of these gases. And on the other hand, on the health issue side, we have like there is possibility of cardiovascular diseases, irritation in the respiratory tracts, respiratory diseases such as bronchitis, asthma, and then finally the cancer also. This can lead to cancer as well. Okay, so the developing a gas sensor is very important. So if you see the sensors history, so like it is starting from kind of the paper, like kind of very long back, like where the miners were looking for some sensors to escape. When the miners are digging, going inside the mines, when they go deep inside, the amount of oxygen will reduce with the distance, the depth, how much they are going inside. This distance, okay, how do they find out? So what do they do is they used to carry interesting like a bird called canaries. Okay, these birds is a kind of a singing birds. It will start making singing noise as we go deep. As the oxygen level reduces, the singing of these birds will reduce. Okay, so this will show that the oxygen level is increasing. This is the first. This is the birth of the gas sensors. Okay, then people use some kind of Davy lamp. This was kind of invented to like this. Essentially, this the light intensity will vary as the oxygen concentration changes. That is how it was being used in the beginning. Then in 1920s, the experimental gas sensors were started appearing. The 1920, the first metal oxide based gas sensor was introduced, which is by Wolfgang and Oswald, and followed by that there are further development happens. The development such as like people use this thermistors and semiconductor based gas sensors are introduced. Then like the first SNO2 gas sensor developed in the year 1960. In 1975, ethanol-based gas sensors were introduced. Okay, so further, if you see that over time from 1960 onwards, there are a lot of development happen. Can all the participants mute yourself? Please. There's a lot of disturbance coming. I'm unable to concentrate. Thank you. So after 1960, there are a lot of work has been done on developing this gas sensor for various applications. So like from 1990 onwards, people started decorating this oxide materials with the metal nanoparticles. Noble metal is used for this purpose. The interesting thing is like the noble metals always have some kind of catalytic effect to increase the responses of the gas sensors. Further, in 2010 onwards, the MEMS-based technology and metal oxide frameworks were invented. Then the recent years, last 1 decade, people started kind of producing this smart materials, smart gas sensors for various application, and also the machine learning has started for this, and the artificial intelligence, which all familiar. Okay, so what is current sensors look like? Okay, this is like kind of on cross-sectional view of the current sensors which is being in the which is there in the market. Here you will see that this current sensor consisting of like kind of a 4 sensing element, okay, and integrated electronics and a casing and the gas inlet and outlet. So what is the 4 sensors? If you see that these 4 sensors will be look like that this Y4, I'll be explaining those details later. Okay, I just want to show you that how it looked like. Okay, this is called a multiplex gas sensor. That is the current technology. Okay, and also this is called a kind of a ENOS. I'll introduce these concepts one by one. Okay. Next comes, yeah, this is like global market. How this gas sensor market is increasing. Like it is, so it was like 2.3 billion in 2024. Now, like it is expected to increase to 3.58 by 2029. Okay. So coming back to the types of gas sensors. Okay, as I told you, we are looking for a active material for the sensor application. These active materials can function in different ways. Okay, so one easy and simplest way is the resistive way. This is called 𝗕𝗵𝘂𝗃𝗃 gas sensors. In this 𝗕𝗵𝘂𝗃𝗃 gas sensor, as you can see, there are like active material which is deposited and interdigitated electrodes. So whenever it is exposed to the gases will be having a kind of reducing nature and oxidative nature. So depending on the type of gases, the material's resistance will change. This is called 𝗕𝗵𝘂𝗃𝗃 gases. This is what we are also studying. And this 𝗕𝗵𝘂𝗃𝗃 gas sensors are the one of the important ones. Like as you can see, these sensors are like easy to fabricate. That's why like more research is being done on this, and also is there like cost-effective scalable. Scalable is the industrial scale of production. It's not like stopped with the one sensor production in the laboratory scale. So in the industrial scale, like there's technology available to make kind of hundreds of thousands of sensors produced at a given time, and it has a high sensitivity towards like target gases, and also there is a real-time detection possible. And finally, it is compatible with the sensor arrays electronic node system, which I will be telling you. So apart from this resistive gas sensors, there are gas sensors which is working by different other physical principle as well. One is the field effect transistor gas sensor, where like in the sensing film, in addition to the source and drain, there is a gate electrode. This gate electrode helps in changing this sensing mechanism, like changing the sensitivity of the gas sensor. That is the advantage of this. And there are acoustic gas sensors available, like when the gas like interact with the active material, the acoustic response of this gas material changes. That will be like studied and analyzed what gas it is. And there is other type is called a capacity gas. Capacity is nothing but a kind of the active material kept in between electrodes. So when the material's property changes, accordingly the capacitance will change. The capacitance will be directly calibrated to give the sensor response. And the next is the inductive gas sensor, the similar principle. And there is the UV visible spectrometer. UV visible to NIR spectrometer is the one which is readily used in the industry for monitoring the atmospheric gas concentration. Okay, I will show you the comparison, like what is the advantages and these things. Because certain applications, some methods are preferred, though it has like other drawbacks, but it is preferred. Okay, I'll come to it next. So there is a thermal gas sensor available, where like this is essentially used for the VOC sensing. Where like you can have both a reference film as well as a sensing film. By comparing this change of the temperature by exposing to this VOCs, the concentration of it is measured. And the electrochemical gas sensors, one of the successful gas sensors, is being commercially available. But one of the only disadvantage of this electrochemical gas sensor is like it's a very expensive one. It cannot be used in several other conditions. And another one is a gas chromatograph. Gas chromatograph is a commercial equipment, like where you can just send the gas inside and analyze it. It's a conventional measurement. Okay, so if you see the 𝗕𝗵𝘂𝗃𝗃 gas sensor, like it will be having 2 electrodes essentially, and the sensing kind of sensing material in between. Okay, and in some cases there will be a heater at the bottom to control the sensor temperature. So all my kind of devices, this is the typical geometry I will be using. There will be some complicated electrodes is made sometimes, some heaters is made sometimes, but essentially the principle wise it is following this. Okay, now this is what I told you. This table compares the kind of what are the different good points and weak points and applications of the different gas sensors. So whatever the sensor we are studying, this is at the bottom, where like we are studying the low cost, simple design and high sensitive gas sensors, and it is affected by the environmental condition. There is a nonlinear response, but this is like in the recent times we are taking care of this with the machine learning. Okay, I'll tell you more about this, how we overcome this weak point. And this can like find application in almost all the fields: air quality monitoring, industrial safety, medical diagnostics, and environmental monitoring. Okay, so when we talk about the gas sensors, what is the key parameters one has to know? Okay, these are all the key parameters one will look for when we are trying to use a sensor or trying to study the sensor. The first property is the sensor response. Sensor response in the case of 𝗕𝗵𝘂𝗃 sensor is the change of resistance. See, you know, as I told you, this is the sensing material between two electrodes. Okay, when you like expose this sensing material to the gas environment, the resistance of this material will change. This change in resistance over this original resistance of the sensor is the sensor response. Okay, that is S is delta R by R. Okay, that is the sensor response. That is the important parameter which you study in the sensors. Next is the selectivity. See, this sensor, this is one of the serious problems in the sensors, because all the gas sensors, like if you have a sensor, like the sensor will have not only a sensitivity to the gas of the interest, gas for which it is being produced or engineered, but it can also have a sensitivity towards the other gases. There will be overlapping signals. So what one has to do is, when you are selecting a sensor, you should have a sensor having a very high selectivity to the particular target gas. Okay, that is called selectivity. And next is the operating temperature. Operating temperature and humidity are playing a major role in defining this sensor property. So usually what people do is they try to optimize the temperature. They will try to work in the room temperature or work in the whatever the temperature which is lowest possible, so that the power consumption is less. Because end of the day, people will be talking about in the terms of expenses. Okay, you have a very good sensor, but it you have to give a lot of power to it. Then like the market value is less for the such a sensors. Okay, so for that reason, people go for the operating temperature, less operating temperature sensors. The next one is the response time. The response time is the time taken for the sensor to reach a 90% of its full response. Okay, this is the response time is the important parameter, because when you expose the sensor to a gas ambient, how quickly the sensor responds to the gas, target gas. That is the response time defines that one. Okay, so this is important property. In addition to the recovery time, when they remove the gas, okay, the sensor should go back to its original state. That's called recovery time. So this parameter also important in defining, because when you are thinking of a gas sensor, you want a sensor which is having a very short response and very short recovery time. So that the sensor is good for the applications, but it need not be limited to this case, because certain case the time doesn't matter, but still you always people look into this number. Okay, so detection limit. Okay, detection limit is nothing but what is the lowest concentration, gas concentration the sensor can measure. Okay, that's very important, because you need to have a sensor which has to measure from a lowest concentration limit to the highest limit possible. Okay, so in that way you can use the same sensor for the different concentrations. And the lowest concentration is very important, because if you see that all these kind of toxic gases, there is always the need for detecting these toxic gases at a very low concentration, because above certain concentration it will be kind of harmful to the human being. That's the reason the direction limit is important. Next is stability. Stability is an important parameter because you develop a sensor, the sensor should have like a constant response over long time. Okay, like you use it, you measure your sensor value, the response value today, like after 6 months, the sensor response should be almost same. Okay, usually in our case, like there will be variation of only 10 to 15%, which we will be including in the program, like because we will study this over time and will include in the program so that this will be corrected in the final out. Okay, so that is a sensor stability, and then the repeatability is like kind of the default one. Okay, when you are doing a different cycles, the sensor should go to show the same response. Okay, now before going to the more details about our work, I just want to introduce you the direction mechanism, which is predominant in this 𝗕𝗵𝘂𝗔𝗟 gas sensors. Okay, if you see this direction mechanism in this all these sensors, like it is the oxide material is there. Oxide material will be like by default will be kind of reacting with the surrounding oxygen gas. Okay, so all the oxide material, this is the usual phenomenon. So when you have a surface, the surface will be kind of always covered with the oxide layer, like kind of oxygen ion layer. Okay, this oxygen ion layer plays a major role in sensor response. Okay, this is the typical reaction happening. If you see here, the oxygen, when it's attaching to the substrate, the surface of the sensor. So there are two types of reaction happening. One is that in the N-type semiconductors, N-type semiconductor material, the this layer, outer layer, will be kind of electron depletion layer. Whereas in the case of P-type semiconductor material, P-type semiconductor sensing material, where there will be a hole accumulation layer. Okay, so this is the what which is always forming in any oxide surfaces. If you have N-type oxide surface, P-type oxide surface. If N-type oxide surface is there will be a electron depletion layer. In the P-type oxide semiconductor, there will be a hole accumulation layer. Now, when you expose these surfaces to this depletion layer, the active material with this type of kind of accumulation layers, electron accumulation, electron depletion layer or hole accumulation layer, then this accumulation layer is the one which is going to interact with the target gases, whether it is you are sending reducing gases, oxidizing gas. For example, if you take gases like CO, carbon monoxide, this is the oxidizing gases. Whereas in the case of if you take gases like hydrogen, it's a reducing gases. Okay, when you have this type of gases, so what will happen? Like this will be like kind of it will be changing this. If you see here, if it's an N-type target material, so the electrical resistance will decrease. Okay, in the reducing gas, in the oxidizing gas, the electrical resistance will increase. Whereas in the case of P-type, the electrical resistance will increase for the reducing gas, and for the oxidizing electrical resistance will decrease. So this is the some basics actually. So with this type of background in the material, now we move on to the different materials which we will be taking for study. So in this our studies, we usually take metal oxides or transition metal 𝗕𝗪𝗔𝗟, that is called TMTs. Okay, the metal oxides are like kind of very important properties on one side. Similarly, the transition metal 𝗕𝗪𝗔𝗟 is having the other important properties. So metal oxides, if you see that, it will be a simple low-cost fabrication. There is a thermal stability, oxygen-mediated sensing mechanism, wide range of directing capacity. It has high sensitivity and is comparable. It is compatibility with the sensor arrays. Similarly, the TMTs, on the other hand, it has a very high surface. The TMTs is nothing but a 2D material. I will be telling you some basics of it as and when it comes. It's a 2D material. It is having a very high surface to volume ratio. It can work in room temperatures. It can have a tunable electronic properties. You can tune these electronic properties by modifying the simple properties, simple structures, surface structure easily. And it has the active edge sides, and it is compatible with flexibility. This flexibility is one of the important aspects, because you always need a sensor which can be fixed on fabric or like on the skin. This is all like a flexible device application. Those cases, the TMTs are very much useful, and it has the potential for selective detection. Okay. So I have told you about the materials, like we are taking oxides and transition metal 𝗕𝗪𝗪. These two materials we are taking, and then further what we do, how do we use that? So this is like kind of a small introduction to the one study which we do with the latter part. This is like the brain inspired, the bio inspired systems are very important things. Like we need to develop devices which can work like a human brain. Okay, that's called bio inspired design. Okay, so what do we do in the sensors? I'll just show you. So whatever the function of the human nose. So essentially what human nose does is like it will sense the molecules, whatever the gas molecules in the ambient, this it will send the chemical signal, and then like it will be like translated into what type of signal it is. Finally, your brain will kind of study the signal and find out what gas it is. So that is how when you go out, if you see there is a pleasant smell, there is a bad smell, those sensitivity we will get only from this function. But the same kind of biological function one can produce by using a artificial olfactory system. Okay, what it does, we have a collection of sensors. Okay, the sensor array, it's called the collection of sensors being shown here. So it will like collect signals from the target gases. These signals, okay, this response will be like collected and feed to the system, and it will extract different features in the sensor. Then it will do something called a pattern recognition. It's called a machine learning. Okay, use the machine learning technique and to identify what kind of gas which is being passed. Okay, so this is the mechanism. This is called a bio-inspired system, and like this is a typical report, like where they kind of imagined this type of electronic nose concept, and they showed, and yeah, these are all like typical examples. Then another application of the gas sensor is the food industry, where like food industry, where like you have a fresh fruit, and like you, when it started kind of spoiling, it will eject, it will give out gases. These gases has to be analyzed to find out how good the fruit is, how good the food or meat or anything. Okay, the food spoilage direction is one of the important aspect in the food industry. And next is the disease diagnosis. Disease diagnosis is one of the evolving concept. You all must be knowing about that point of care devices. What it does is like regular blood test, like you just go a prick or like use a syringe and draw blood, and then it will go through different analysis and find out what is that in the blood, kind of the different constituents they find out. The same way, the interest is to analyze the human breath. Okay, so how it does is like you make a person to breathe in and breathe out heavily on a kind of a sample collecting bag, and this sample will be fed into a instrument. Okay, this instrument now will analyze what all the gases in the breathe out air and give you the details about what all the disease a person may be having, or like these systems are being developed, and some cases it has been used successfully for some applications. Okay, so this is essentially a disease diagnostics. Next is the environmental air pollution monitoring. This is one of the application needed for the industries. As I told you, the industries like give out like different toxic gases and VOCs, and it needs to be continuously monitored. So this monitoring, like people depend on something like kind of the ENOS kind of arrangement. How it works is like it has a collection of sensors, and each sensor is selected to different gases. So this ENOS system will collect the response from all the sensors. This signal, the response signal, will be fed to a computer programs. There's a machine learning programs available with a lot of library files with recorded data. So this will compare with the existing data, recorded data, the previously stored in data, and then predict what type of gases are present. There will be a quantitative analysis also possible. Okay, these are the three major applications, as I told you. So there is a 𝗕𝗏𝗄𝗏 direction, disease diagnostic, and environmental air pollution monitoring. These three are the major applications where the gas sensor are being used and is being developed for further improvement. Okay. Now move on to our research work. Like what we do is, like, if you see, I work on oxides. I told you in the beginning. So in this oxide material, like we have in this study, we have taken a spinel structure oxide, that is a zinc ferrite. Okay, zinc ferrite is like kind of a material which is having a spinel structure, is one of the cubic structures with the tetrahedral and octahedral sites. So depending on the ions occupying this tetrahedral and octahedral sites, the property changes. What we found is, like, we take the normal spinel and convert into a mixed spinel. So in this mixed spinel, we found that, like, it is having a better stability, and it having a controlled cation distribution, and it's widely used for. It can be widely used for various applications. It has a balanced electric content. That's the main aim. The reason people choose the mixed spinel for this study. So what do we do? So what we do is we prepare this compound first. We can prepare the compounds by a chemical methods called a co-precipitation method. This is one of the chemical reaction where, like, you have a chloride and acetate to undergo a reaction at different temperatures. Okay, and with the addition of sodium hydroxide, one can produce the zinc ferrite. Okay, then you take the as prepared one and heat at different temperatures. This is called different calcination temperatures. By changing the calcination temperature, we can tune the percentage of this like tetrahedral occupation or octahedral occupation in the different sites in the crystal lattice. Okay, if you see that, like, this crystal is having a spinel cubic structure with space group of Fd3 So the crystallite size increase with the calcination temperatures, and what we found is, like, we are varying this degree of inversion from 0.78 to 0.39 by varying this calcination temperatures. So what it means is, like, if you see the structures, so the Fe ion or zinc ion are sitting at different places. So if you see here, the Fe ions are mostly occupying the octahedral site, and zinc ion will occupy the tetrahedral, that is yellow one. Okay, the zinc ions are sitting. The mixed phase, you will have the metal as a Fe ion is sitting in the octahedral as well as the tetrahedral site. Okay, if it is if the Fe ion is sitting only in the octahedral site, it is a normal spinel. If Fe ion sitting in the tetrahedral site also, that is this blue and the yellow ones. If it is sitting in both the places, then it is called the mixed spinel. That is where the name comes from. Okay. Now move on to the further characterization. We do kind of XPS analysis. XPS X-ray photon spectroscopy. I hope you are all familiar with this. It's essentially like you take a compound and heat it with the high energy X-rays. Then, like, this material will be kind of ejecting photoelectrons. These photoelectrons are analyzed. So depending on the energy, these photoelectrons, like, will be that photoelectron data will be analyzed. So usually, like, the data will be like emitted radiation intensity as a function of binding energy. Okay, these are the data. I don't want to go to the details of it. It is like calculated from the X-ray energy, kinetic energy, then finally binding energy to be calculated. So what data you will get from XPS data is, you will get a photoelectron intensity as a function of binding energy. By analyzing this data, one can find out what are the elemental composition in a material, because this is one of the important study for the material characterization. By doing this study, so we kind of showed that, like, the occupancy of the Fe3+ ion and the zinc 2+ ions in the element. Okay, this, like, we have established by using this study. Okay, further structural morphology we analyze by using microscopy technique. Microscopy, we use electron microscopy and scanning electron microscopy and transmission electron microscopy. So this basic general is, like, you must be familiar. The electron microscopy is like the technique where you use the radiation which is, like, having a wavelength close to the features in the sample, features of your interest. Okay, in these cases we are interested in the atomic level feature, like going to the nanometer features. So for that reason, one has to use the electron microscope. So electron is used as a radiation here. So the electron will interact with these features and give the secondary electrons or backscatter electrons. Those secondary electrons will be analyzed using detectors and give the. That is how the electron microscope works. So this works in two modes: the scanning electron microscope and natural electron microscope is one of the sophisticated instruments where a thin layer of your sample is kept at the electron beam. So whatever the electron beam which is incident on the sample and which is getting transmitted, these transmitted electrons will be analyzed with the suitable detector. Okay, these detectors will give you the picture of atomic arrangement. Okay, so the atomic arrangement, whatever I'm saying is highest resolution level, but for the like kind of our experiment for our research purpose, we go for a lowest like some slightly less resolution where you get a this type of particle structure features or like kind of lattice fringes, everything you'll get. Then you can one can do a diffraction experiment. This electron diffraction, same as the lava pattern you use for the X-ray diffraction. This one I mean here. Okay, this is the electron diffraction data where like you have taken a sample and make a electron beam to incident. Now, because of that atomic arrangement, it will produce the diffraction pattern. This diffraction pattern will be analyzed. This is called electron diffraction. This is same as the lava pattern. Like it will produce a kind of a concentric rings similar to like corresponding to different lattice planes. Okay, these basics I don't want to go to the trick. It's the same as the black X-ray diffractometer. That's what we just remember that concept. Okay, so this measurement will tell us like how this particle size of our samples are there and how this crystalline structure of these particles are there. Okay, these two things we establish using this, and then like we will calculate the average particle size for the different compositions. Okay, now coming to the gas sensing study, as I told you, our configuration is like we have a 2 electrode and active material deposited between this 2 electrode. Okay, in order to further improve this and the gas and the material interaction, what we do is we make something called interdigitated electrode. Okay, this is one of the important concepts. This is one of the important thing for the devices where if you see here is essentially a 2 electrode system. This is 1 electrode and this is 1 electrode. So instead of just keeping a 2 like vertical electrode, we'll have something kind of interdigitated. It's like 2 fingers going like this. This is called interdigitated. So advantage of this is like you can have a more like kind of interaction of the active material with the gas molecules as well as the whatever the produced charges, which can be taken to the electrodes easily. Okay, that's the advantage of this. So most of the gas sensors, this type of interdigitated electrodes are used. Okay, so we take this interdigitated electrode. In this case, like we have a gold layer electrode, and on the top of it, we'll bring a active material, mixed zinc ferrite, whatever we developed in the previous slides I showed you. So those material, like usually, like we will just do the drop test. It's very simple because we have to do make a method which is viable for the industry. Okay, so we go for a simple one. We don't want to use a high-fi like deposition technique to produce these films. So these films, what we do is we take the electrode and drop cast this material. This like this drop casting, advantage of this drop casting is this can be readily used in the industry easily. So we take the nanoparticles in a suitable solvent and take a stock solution. The solution, like every time, we'll be just taking a drop of it and put it on this electrodes. Okay, that's how it's being made. Okay, so this is how it looks like. So finally, whatever the produced sensors, it will be look like this. Okay, the real sensors, I'll do the photograph. I'll show the photograph. This is schematic, but essentially it will look like this. Okay, then go to study the response of for the different gases. So in this case, we have used the NOx, that is the NO2 and the NO gases, and we vary the different concentration and study the response for this all the samples. So we found that the sample calcium at 500 degrees is having a much better response. So we use that sample for the further study. Okay. So if you see here, our further studies will be looking like this. So what we do is like you take the sample and we allow a pulses of gases. Okay, like what you do, these pulses are not like kind of a microsecond or something like it. These are kind of minutes. So this will be usually automatic valve will be there. You can control the timing. So the valve will open, allow the gas, and the valve will close. Okay, it's like that. It's automatic arrangement. So what it does is like you just allow the gas to pass at this moment. Then when it reaches a maximum, then cut the gas supply. Okay, that's how these measurements are made. So this, like if you ask, you can see we can have a different concentration. See how this concentration produced. This is another important thing. So we want to study these gases at a different concentration. So the different concentration, what I mean is, we take these target gases and mix with the synthetic air. Synthetic air is nothing but we collect the air from using a compressor and pass it through different filters to remove all the moisture. So dry air is called a dry air. That's called synthetic air. There's no moisture in it. That's all. So we mix these target gases with this synthetic air, that is the dry air, and pass it to the sensor. Okay. So this sensor, this way we can vary the concentration of the target gases. Say the concentration is varying from 30 ppb, 60 ppb. This is like a kind of a calculation the computer will take care. We have a mixing chamber, like so the known concentration of gases, the target gas under the dry air will be allowed to the mixing gas, the mixing gas chamber. The mixing gas chamber will mix it and will produce the gas. So that gas we'll use for the analysis. That's how it is. Okay. So we are kind of gradually varying the concentration, like 60 pp, 30 ppb, 60 ppb, 90 pp, 100 pp, 150, up to 1 ppm level. This measurement is done. So similarly, we do the measurement for NO gas, the NO2 and NO gases. The measurement is made, and further study, like we find the limit of detection. What is the lowest limit the sensor can detect? So we'll find out. Then selectivity. This is one of the properties which I showed you. This is called a selectivity. So if you see that, so you take this response, we allow different target gases and see that how it's responding. So in principle, like if the sensor is selective to a particular gas, we should have a response like pretty above 90 or 95%, and all other gases should be less than 20. That is the usual concept. Okay, all other gases should be less than 20. That this sensor should be having a response above 90 or 95. Okay, this is what the usual procedure we follow. So this is like in this case, like this sensor is responding only to NO2 and NO. All the other gases like just CO, NH3, SO2, and CH4, the response is low. Okay. Now come to calculation of the response and recovery time. Response and recovery time, as I told you, like when you pass the gas, okay, how quickly the sensor will respond. Okay, this is kind of up to this is the time taken to reach the 90% of the maximum response. So in these cases, if you see, like we have a very good response time of 7 seconds, and the recovery time is about 71 seconds and 92 seconds. Okay, this is like relatively good for the industrial scale, because whatever the current sensors which is having like a response in minutes actually. So more than 2-3 minutes. So our sensor is having a better response. And these are the stability over time. Okay, this is called the long-term stability. We study the sensor, okay, for particular concentration for different times. Okay, for different days, like every alternate day, we will measure it and find out what is the response. And this is the cyclic stability. Cyclic stability is nothing but you take a response and continuously vary the concentration, see how the response is. Like if you see here, the sensor is having a very good response to this target gas. This is what is being shown here. Okay, that like it is like within that 2-3% variation it is there. Okay, and we do kind of a JTL calculation to establish why this material is having a higher response, higher response to the particular target gas. We find by calculating the absorption energy for this material. So if the absorption energy is the kind of having a very high for this mixed, this calculation shows that this taken phase mixed zinc ferrite, the absorption energy is very high. This shows that this will having a much higher response compared to the other phases, normal phase or other phases of the same compound. Okay, and we kind of show the practical applicability of these sensors by preparing this type of a prototype. This prototype, what we does is we take the sensor and mount it in a platform along with the immunity sensor, and is controlled by the Arduino. Okay, the Arduino is shown here. Now we expose to different ambient. In this case, we have exposed the sensor to this car exhaust. Okay, and we studied how how much NOx is present in this sensor in the car exhaust. By knowing this standard values like calibration, you can calculate how much amount of NOx present. In this case, car exhaust is having 2.7 ppm of NOx gases. Okay, so this is the comparison table. This is essentially comparing our data with the literature. Okay, how our data is comparable to literature. If you see that this is having a kind of a very good response and good response and recovery times, and it is having a lowest direction limit of 10 ppb. And the important aspect is this can be used at room temperature. That's one of the advantages. Okay, so this is kind of a summary of this work. We use the zinc-ferrite for studying the NOx gases. Actually, we can measure these gases kind of having a lowest direction limit of 30 ppb, and this is the kind of this can be used for a different concentration as well. Okay, this is our publication. Now I move on to the next material. In this study, we have taken a kind of a two material and make a heterostructure. It's a kind of a composites made. So the two materials what we have considered is nickel oxide and neodymium dope nickel oxide. Okay, NdNaO3 and NaO3. Okay, this is the compound we have considered for this study. So this compound, if you see that this is kind of a FCC structure, and which is having a p-type kind of semiconductor nature. And if you see here, if you see here, we kind of optimize the preparation by a simple co-precipitation route. Again, nickel chloride and neodymium acetate were taken as a starting material. By mixing with the NaOH, we can make this solution. Then we centrifuge will make the nanoparticles. These nanoparticles will be further dried and annealed, and to get this type of nanostructures. Okay. Again, as usual, we do characterization by using X-ray diffraction, and we shown that how these two phases are present, the NaO and NdNaO3. So we vary this concentration by showing that the NaO concentration increasing with the increasing the product. Okay, so this is ratio of the molar ratios we are changing in the starting compound. Is the Nd and NaO is 0:1, and it's varying from 0:1 to 1:1. Okay, then for the each step, the product we have observed a similar one. When the NdNaO3 compound composition increases, that NdNaO3 peak is increasing and NaO peak is decreasing. Finally, this end compound, where that is the 0.8, 80% of NdNaO3 is there. If you see here, this will be kind of a mixed phase. This is a green one. This green one is the mixed phase. That is a mixed composite NaO and NdNaO3 X-ray diffraction, which shows the peaks correspond to both NaO and NdNaO3. Okay, this we do the basic calculation, characteristic crystal size from the X-ray peak peak width. We can calculate the crystal size. There is a formula called the Scherrer formula, which is used. Using this formula, by using the peak width of the any X-ray peak, one can calculate the crystallite size. So that is what we apply to calculate the crystallite size. And we have done X-ray photoelectron that's called XPS, to analyze the chemical composition and find out how much the ratios are present in these compounds. And this is compared with whatever the starting composition we have taken. Okay, and then the morphological characterization using the electron microscope. This is the SEM and TM image. This is the SEM image, the scanning electron microscope image. This is the TM image. I told you this basics of this. Essentially, this is kind of this high resolution. You just imagine like a high resolution microscope which is showing a very small features. Okay, so if you see that in this compound, this is how the nanoparticles are there, and the crystalline orientation of these nanoparticles we found using this TM. These are all the crystal planes present and electron diffraction, which I showed you for the previous compound. Similar method, we can establish the kind of crystallinity of this material at the nanoscale. Okay. Now move on to the sensor response. Like this response, unlike the previous study where we have developed a room temperature sensor, here we need to have some heating. That is room temperature. This sensor response is very poor. So we are optimized like 100 degree centigrade, like the sensor is having optimal response. So at that temperature, we study the different materials. Okay. Here, like as I told you, here we have used this type of sensor configuration. This is the kind of a commercial casing available where like there is a ceramic tube with a nichrome heater in the center. Okay, there are two gold electrodes which is attached to the electrical wires. Now what you have to do is we have to like drop cast our material between these two electrodes. Okay, that's how it is. This kind of casing is available commercially. We have taken that casing and developed the sensors because we need the heater for this sensor to work. Okay. Similarly, like we have done different concentration studies. Like from that we can find out like response and recovery time and what is the lowest concentration the sensor can measure. If you can see here, this sensor can measure up to 450 ppb. And another important thing, as I told you, this is needing this sensor operation needs heating. So we do this sensor studying at different temperatures. Like so, we optimized that. We found that around 150 degrees centigrade, 140 degrees centigrade, the sensor is having a optimum response. That is the highest response possible. So at that temperature, we have done the other calculations. Other gas analysis. Okay, all these gas analysis are done at 140 degrees centigrade. Okay, again, like we do a noise study and lowest limit of detection studies and response and recovery times. If you see the response is like 132 seconds and recovery is 277 seconds. And the cyclic stability, this is the long-term stability, and this is the selectivity. These are all things like basic characterization for the gas sensors I will do. I told you in the beginning. Okay, then like we compare this data, this sensor data with other literature. This is where like our sensor is there. So we have an optimal temperature of 140 degree centigrade for usage, and as the lowest limit of detection possible up to 320 ppb. Okay, that's what we are showing here. Next, we do a theoretical calculation, which from which we kind of find out like why the sensor is active to these gases. Okay, that's the one we do. So in this sensor, as you can notice, I forgot to mention this sensor. We are studying SOx gases. Okay, SO2 is the gas which we have in the lab, which we have used, as a target gas in this study. Okay, so this theoretical study, what we do is like we take these different surfaces, the composite surfaces, and find out how this like kind of interface between these two surfaces, two layers will form, and accordingly how it gives the higher activation and higher absorption energy for the SO2 gas. Okay, that is what the theoretical calculation will give us. Okay, this is basically to understand like and correlate how our sensor response is good for the particular gas. That's the reason the theoretical studies are being made. Then the practicability test, as usual, like we develop a portable sensor like this. This NIO and NMO based sensor here, and humidity sensor, and it is sent to the Arduino. Okay, this is how the sensor look like. The sensor response with different concentration show here, and we kind of show some videos and show that like how good, like if you see that they said like as the concentration of that SOX increases, some at a particular time, like this sensor will show a kind of a level. The level is raised to a kind of a alarming level, and after some time, like the level will increase. When the concentration increases, it goes to the alarming level. It's a danger zone. Okay, so essentially this shows like the sensor, what concentration the sensor is showing the danger level. That's what we are establishing with this test. Like usually this type of prototype is used to set up a small gallery in our center. Like this gallery will be open to the industries which you are visiting and having a look. So those industries who are interested will be like, they will be taking this technology and later develop the sensor using this technique. Okay, that's all. So these are all the conclusion of this work and the publication. Let me move on to the next device. So next material. So in this study, we have used here 𝗕𝗪𝗏𝗔𝗍. That is a transition metal 𝗕𝗪𝗏𝗔𝗍. 𝗕𝗪𝗏𝗔𝗍 is nothing but a graphene-based material. It's a 2D material. 2D material is like if you see that each layer is having a kind of a covalent attraction, in-plane covalent attraction, and between these planes there is a van der Waals interaction. This is the specialty of the 2D material. Okay, so each layer, so like graphene is a very famous one, you might have seen. The single layer of graphene is taken and their properties will be found that it is having a superior mechanical and other electrical properties. Similarly, it has been studied for the different TMDs as well. That is the transition metal 𝗕𝗪𝗏𝗔𝗍. The 𝗕𝗪𝗏𝗔𝗍 is the MOS2. This is one of the famous compound. In this MOS2, like generally it will be in the 2H phase. Okay, what is 2H phase? Is nothing but like how the layers are arranged. It's like if you remember the solid physics, there will be HCP and FCC stacking in the material. Like there is a AB stacking and ABC stacking. This type of stacking you might have heard in the solid physics. So the same concept applies here. In the case of the regular 2D material, it will be in the 2H phase. 2H phase is nothing but a AB configuration. Okay, that is like if you see here, like the A atom there, B atom is occupying here. Next, the A atom will come. The A atom will be just below this one. Okay, so this is the regular configuration of the 2D material. So MOS2 fall in this category is called a 2H phase. That is a trigonal prismatic phase. Now, what we do in this study is we modify this kind of the few layers, because you take the pure MOS2, that response is not suitable for the gas sensing. Like maybe I have shown some examples here. Like the response is not very much suitable for the gas sensing application. So one has to do some kind of modification in the surface or edges to tune these properties which is suitable for the gas sensing applications. So one way to tune, because this tuning this 2D materials is a very vast study. People use different methods. Like usually these 2D materials are prepared by some methods called chemical vapor deposition method. Okay, so they take a material in different solvents and they operate the solvents, and the operator solvent will be carried to the substrate and deposit this 2D material at a kind of a maintained conditions. I don't want to go to the details because we are not using this type of CVD method in this case in our studies. So what we do is we do a method called exfoliation. Exfoliation is nothing but you take a bulk MOS2 and peel off the layers. Okay, this is called exfoliation. This is called, like the famous method you might have heard is something called a Scotch tape technique. In the Scotch tape technique, what they do is like they take a graphene, like kind of single crystal graphene they put a tape on the top of it and peel it. So every time they peel a tape from the graphene, bulk graphene, 1 or 2 layers of graphene is sit on the Scotch tape. That Scotch tape you just put on the other substrate and press it, the graphene will be transferred to the substrate. This is one of the well-known techniques. It's called a Scotch tape technique. This method is called exfoliation. Okay, please remember the word exfoliation. So what it does is you take a bulk where there are layers of this material is there. It's called bulk chalcogenides. This bulk material we put in a sonication, something called ultrasonication. Ultrasonication, you must have heard in the chemistry lab. This ultrasound is sent to this solution medium, and it will interact with the solution medium, and it will kind of having a high energy to split the particles. Okay, so the same technique is used. Like this, all optimized by one of my collaborator. I was just taking a sample from him. So he has optimized, and he can make a kind of a single layer or bi-layer kind of a MOS2 nanostrips. Okay, so in this case, like whatever we have used, because we need layers for with certain property, we need a sample with a certain number of layers. Then only we can modify few layers for our application. That's why, like in this case, like we are asked for like something like more than 10 monolayers. So he has produced some method where he produced like this, whatever the layer he has, each one is having some 13 monolayers of it. That's the sample we have taken for the further study. These are all the basic characterization, how it will be characterized. This is very interesting. Like how do they characterize it? What do they do is they take this 2D material and put it on any substrate and then do a atomic force microscope. Atomic force microscope is nothing but a sharp tip with the atomic resolution. The tip resolution is in the nanometers, like sub-nanometers. Like then this tip will be moving on the substrate. It will scan. When they scan, the tip movement will give the surface morphology. So when we have this type of layers of this 2D materials on the top of it, then the tip will just see how this layer is there. Like if you see that this is this photograph, if you see here, this is the AFM photograph. Now you just do one like a height profile of this image. The image will give you the height of the layers. Okay, so in this case, let's layer height is about 7 nanometers, 7 to 8 nanometers. That is about 13 monolayers of MOS2. This is the sample we have taken. Now come to our studies. What we do is like we take the pure MOS2, like liquid phase exfoliated MOS2, and did the gas sensing. Like we found that this is not having very good response to any of the gases of interest to us. So what we did is we tried to modify these surfaces. So one way of modifying this 2D material, as I told you, these all like the layers, in plane layers are covalently bonded, and interplanar interaction is the van der Waals interaction. So this is like it's not easy to do with the regular route. So what we do is we do some kind of a plasma treatment route. So what it does is you take this layer and expose to the plasma, oxygen or argon plasma, and modify few layers of it. So as you can see, this modification, like either it will when you use oxygen plasma, it will produce a MOS2 layer. Okay, when you use the argon plasma, it produces a kind of a different phase of MOS2. I'll tell you the details. Okay, and also it is having two different types of semiconductors, so N type and P type, which we have analyzed. So whenever we do with the oxygen plasma, we have a MOO3 and MOS2 interface. Whenever we have a argon plasma, we have a 1T phase of MOS2 on the produced MOS2. That is 1T and 2H MOS2. So so in the case of 2D materials, one of the important experiment one has to do is the Raman spectra. Unlike the other materials where we depend on X-ray diffraction, electron microscope, other things, the 2D materials, the important technique people use is the Raman spectrometer. Raman spectrometer is nothing but like we just pump in laser light of particular wavelength, okay, particular frequency, and the Raman effect says that due to the change in the polarization of the samples, it will produce the Raman lines. It will produce the different scattering lines. This scattering different, I meant is it produces the scattering light, that light which is coming from the sample, which is having a frequency different from the incident frequency. So when you analyze this frequency is corresponding to different energy levels, okay, polarization levels of the sample. So that is the Raman spectroscopy. By analyzing this Raman peak, one can find out what is the phase in it. Okay, usually this is the fingerprint method people use for 2D material characterization. Raman spectroscopy is one of the important techniques one has to use for analyzing 2D material. So when you do Raman spectrum, similar to X-ray diffraction, where like you will have a characteristic peak coming from the different lattice planes. Similarly, if depending on the different structures, different crystallography structures, this sample will give different Raman peaks. Okay, that peaks are corresponding to different energy levels. Just like in this case, it is the E12G and A1G modes are there. This is a different vibration modes present in the samples. This is the fingerprint modes. So for a particular 2D material, the sample will produce the peak at a particular energy level, particular wavelength level. This case is called Raman shift. Okay, so here this is the exfoliated sample, the bottom curve. If you see here, this is exfoliated sample. Now, when we react it with the argon plasma, it produces peaks which is corresponding to 1T MOS2. Okay. Similarly, when you are having a reaction with the oxygen plasma, it produces the MOO3 phase. So essentially, we are getting a 1T MOS2 and 2H MOS2 one sample. The another sample MOO3 and 2H MOS2. Okay, these are the two samples we produce. These samples are characterized by using a electron microscope technique, and we show the different phases are present. And this is the HPS analysis. HPS is similar structural characterization we do, like kind of finding out the different chemical composition. Okay, and then we take this sample and like as usual, we drop cast or spray coat these samples onto the interdictated electrodes. Okay, these interdictated electrodes are further used for the sensing studies. So if you see that, like whenever you have the MOO3 and MOS2 interface, this sensor is having a response to ammonia. And on the other hand, if there is a 1T MOS2 and 2H MOS2 space interface there, the sensor is showing a response to NO2. Okay, this is the important thing. Okay, by just modifying the different layers, like see, essentially we are taking a 30 layers of MOS2 and a few layers are converted into MOO3 in this case, one case, and 1T MOS2 in other case. Okay, by changing that few layers or at the boundaries, we can vary how this type of gas interaction changes. MO3 MOS2 interface, which is having a P-type nature. P-type is the one which is having more holes. There's a P-type semiconductor nature, is showing a good response to ammonia. And on the other hand, the 1T 2H MOS2, which is a N-type semiconductor, which is having a good response to NO2 gas. Okay, this is the important thing. By just tuning, by changing the plasma, we can tune these interfaces and make this material response to different types of gases. Okay, and similarly, like we do the different gas response studies, a different concentration study, and find out limit of detection and other things. These are all the characterization which we do, and selectivity is the one which property we study. Like as I told you, that oxygen treated one is showing a good response selective to the ammonia gas, and below the NO2 treated, argon treated one showing a good response to NO2 gas. Okay, these two are showing a good selectivity to the two particular gases, and we calculated the response times, cyclic stability, and long-term stability. Everything we calculate, we compare to the literature, and we do a theoretical calculation similarly with like to calculate the absorption energies and to find out why this material are responding to the particular gases. Okay, this work was done in collaboration. Okay, now move on to the practical applicability studies. Like again, we developed a prototype and we showed again, like we collected samples from the vehicle emission as well as the other meat and fish emissions and analyze the gases. You see here, like we have done fish and chicken spoilage tests and show that above, this is kind of a threshold kind of one. Above certain limit, the spoiling is more. Then there is a NO2 or NH3 gases. NO2 NH3 gases coming from the samples will be increasing. That will tell you like how good or bad your meat is. Okay, this response, if you see here, like when they start the chicken, I think in this case it's showing here good, like it's good. Okay, like every 15 minutes you will open it and expose to the sensor, like it's good. But after some time, if you see that this one, so it shows that meat is spoiled. Okay, it shows the warning that the meat is spoiled. Okay, let me go to the next one. So these are all the conclusion from the study. Then the other 2D material we have studied is the VS2. Like this is the vanadium sulfate samples. So in this case, like this method is developed, that basic VS2 is developed by one of my collaborators, Dr. Subhash. So what we do is we take this VS2 sample and react with the H2O2, and this leads to certain like kind of oxide droplets on the top of this VS2 sample. Okay, this is the typical sample we make. So if you see that there's kind of a flower like morphology, VS2 is there, then it is kind of decorated with the oxide particles, that is VO2 particles on the top of it. Like in this case VOX, we don't know exactly the VO4 or VO4. Okay, so this is how the real sample look like under the electron microscope. This is the scanning electron microscope as prepared sample, and then increasing reaction time. We have increasing reaction time of 30 minutes, 10 minutes, 30 minutes, and 90 minutes. If you see here, these all like kind of a flower-like morphology is there, and with the time, these flowers are converted into droplets. Like the droplets start appearing on the top of it. Okay, this is how it will be. Now we analyze it further with the TEM. We show that both the VS2 and VOX spaces, sometimes VO2 or sometimes V2O5. Okay, those spaces are present in these samples. Okay, and we further do X-ray study and X-ray differential study, Raman scattering study, and the binding energy X-ray studies to analyze these samples and go into details of it. Then coming to the gas sensing, like we kind of did the first measurement on all samples with 4 ppm of NH3, and we found that the gas is showing a good response, like the sample with 10 minutes of reaction, 10 minutes of conversion to VOX is showing a good response. So that sample will go take it for the study. The limit of direction is 300 ppb, and the cyclicity and cyclic stability and the long-term stability, everything we are showing in this. Okay. Next, we developed this type of prototype, and this prototype like analyzing the different gases. Okay, and the important thing is we have developed like sensors to which put on the human skin, or like sensor to like use for the smart home applications, and kind of sensors deposited on the fabric. Okay, this material, that's one advantage of the 2D material I told you in the beginning. This 2D material can be kind of deposited as a flexible samples easily. Okay, then they are flexible samples you fix on the fabric, and you can make a sensors out of it. Okay, this is how the sensors works actually. Like you have the sensor like this, then you expose to NH3, and if you see here, like after sudden exposure, they show warning that NH3 is exposed on this device. Okay, this is like one of the study we have kind of just got accepted. Next, we move on to the sensor. This is kind of a last part of my study. I hope I will take another 10-15 minutes. This one, like as I told you, our interest is developing a sensing platform. Okay, sensing platform is nothing but mounting the sensor which is responsive to different gases on a single platform. Okay, essentially, in this case, it will look like this. Okay, this is one platform where 4 sensors we have taken. Okay, 4 sensors, like we have taken zinc ferrite sample and gold decorated SnO2 samples, and we have taken NaNO3 sample and the MO and MOS2 interface samples. Okay, this like for the different gases. Okay, so now this sensor along with the humidity sensor, it's fixed. There is a microcontroller present there, and we call this sensor as a sense array. Okay, this sense array we use for different gas cancellation. I'll go to the details later. Before that, this is showing a characterization, which anyway I have showed you in the individual studies. This is a basic characterization we have studied, carried out for the different sensor material. Now, coming back to this data, this is one of the important data. What we do is, we have 4 sensors which is fixed onto a sensor platform. Now, what we do is, we allow different gases. In each first set of studies, we pass individual gases onto sensor array and study the sensor response. Okay, the different concentration and individuals, 4 sensors, like how it is producing. Okay, this is how we vary in the concentration, how the sensor response is. Okay, similarly, we go for this is for CO gas, this is for the NH3 gas. NH3 gas with the increasing pulse of concentration, like exposed to the 4 different sensors. Okay, so I hope you all could follow, because this is an important study. So we develop a library like this. Okay, so we make a sensor, 4 sensors in a platform, and every time we pass a single gas with different concentration. Okay, we collect the data. Okay, this is for the 4 different gases: CO, NH3, NO2, and SO2, individual gases. Now we do a principal component analysis. It's a machine learning algorithm we do, and find out like how accurately one can calculate identify these gases. This is for the single gases, and do PCA. This is the principal component analysis. This one is the multi-layer perceptron model. Okay, this is the long and short-term memory model. Okay, and long and short-term memory model is nothing but you pass a sensor, pass pulse of gases, or short duration and long duration. By studying that, analyzing this response, one can find out how good the sensor can be used for the identification of the mixture of gases. That is the interest. This is called a long short-term memory model. Next is the convolutional neural network model. Okay, these are like computer programming. Essentially, like we collect the data. The data is fed to different programs and analyze it with how accurately you can calculate the gas concentration. That is what it does. Next, we go to the mixture of gases. Mixture of gases, like the 4 sensor, and now first we pass the individual gases. Now we are passing mixture of gases. First gases, mixture of 2 gases, like NO2 CO response and NO2 NH3 response. Similarly, SO2 CO response and CO NH3 response. Similarly, the other permutation combinations, NH3 SO2 and the NO2 SO. Now you use the principal component analysis and find out how you can accurately define the gas concentration. Okay, so principal component analysis is nothing but like kind of different concentration, all the data put together. It will reduce the dimensions and find out like how easily one can predict how much accuracy one can get the data. Okay, these are all like different models we applied and do the prediction. Now we take a mixture of 3 gases. Okay, similar analysis. Okay, and with that, like we have made a summary. And in this study, what we have done is we have used 4 different gas sensors, okay, and having a mixture of these four gases, four target gases of interest. And now we have analyzed with the different computer programming and predict the gas concentration with a certain accuracy. So how much we achieved so far is like we can predict the gases up to 98% of accuracy. That is the success so far. Like this is the ongoing work. Like we are like kind of further improving our program and further adding more sensors, more gases is ongoing work. Okay. Similarly, in this study, like we have combined sensor, gas sensor, and another one called resistive switch. Okay, so this is kind of a artificial olfactory nociceptive system. So what it does is, you have a gas sensor. The gas sensor will respond to particular concentration. Now you have another switch added along with this gas sensor. So you tune the switch in such a way that the sensor will be responding only at the particular voltage, particular control. So till the time the sensor will not respond. Okay, this is the artificial olfactory nociceptor functions. So I'll just show you like how it is working. So in this case, like what it does is, like when we have a concentration above certain threshold, maybe I'll show you. Yeah, okay. Before going to the detail, I'll just show you how this system will look like. So in this system, like we have a gas sensor which is seriously connected in series to resistive switching device. Resistive switching device is nothing but a device which is having a multiple resistance state. In this case, like we are having two resistance state, we can take the device to a low resistance state or a high resistance state, applying a bias. Okay. Now by connecting this in a series, so what is happening? This is what the interest in this. Okay. So before going to that, I just want to briefly tell you about this resistive switching device. This is called threshold switching memristor, where like this is kind of volatile switching. What will happen is, like we apply a particular bias, the memristor will go from a high resistance to a low resistance state, and when we remove the bias, that resistance state will drop down. Okay, this is kind of a volatile memory. Okay, this is how this works. I'm not going to the details of this. This is another kind of my research interest. But in this work, I'm combining both this resistive switching as well as the gas sensors. Okay, this is how the device will look like. Okay, now what it does, like you have a bias, okay, bias of like 0.8 volt. The sensor is not responding to gases. Okay, but when you increase the bias, okay, at particular biasing, say about 1.2 volt, the sensor start responding to 10 ppm of gas. When you further improve the bias, the sensor is responding to 5 ppm of gas. And when you further improving the bias, like you go to 3.2 volt, for example, then the sensor will start responding to very low concentrations. Now we can change the bias and see how we can kind of teach the sensor, like gas sensor, at what concentration it has to measure. Okay, this is a kind of a olfactory nociceptor system. Like this is again the ongoing work which we are doing it. I just want to give you a brief summary. Okay, now I almost come to the end of it. I hope I'm on time. So to briefly summarize the work, like in our studies, we develop different materials, okay, for like oxide materials and transition metal dichalcogenic materials, and for the different gases for gas response, developing a different gas sensors material, and then further use this gas sensors and develop this type of electronic nose kind of applications. This is what our interest is. Okay, I have come to the end of it. Like, so I have to acknowledge my funding partners. I have kind of having a fund project from ANRF, okay, and which is also supported by a Tata Steel project. Actually, this is a ENOS concept, like we have first developed for Tata Steel because they want to use this type of sensors in their factories, steel factories. That's how this work was started. Then I have some project with the Indo-French collaboration. This is my research group. Okay, 𝗕𝗫𝗙 is the one who has done this work. Okay, thank you very much.
Wonderful session, sir.
Thank you.
Thank you so much, sir, for this enlightening and engaging session. And I especially very much like that mimicking olfactory systems for enhanced gas detection. That is ingenious. Thank you so much, sir. On behalf of both of us, Dr. Kshitij Kumar Das and myself, and all our wonderful participants, we sincerely thank you for sparing your valuable time and sharing your expertise with us. Participants, do you have any questions for sir? Okay. Sir, in chat, 𝗕𝗵𝘂𝗶𝗵 is asking, could you please explain the fabrication method of the interdigitated patterns, whether photolithography technique was used or any other method?
Good, actually. This one, it can be used by photolithography technique also. It depends on the what dimension you want. See, photolithography is needed when you are fabricating something in the micrometer length scale. Okay, if you are not interested in the micrometer scale, you can use a simple shadow masking technique. Okay, what it does is you will have a mask made of a metal. Okay, then you just keep it on your substrate and deposit metal over it. Okay, so by this way, you can easily prepare this interdisciplinary approach. Okay, usually for the metal preparation, we go for a kind of a buffer layer, kind of titanium buffer layer, and then gold deposit. So that will give a very good addition of the metal onto the substrate. Okay, so both the photolithography can be used, as well as the simple shadow masking technique also can be used, depending on what dimension one is looking for. In our cases, it will be if you we are not in the micrometer range, in the millimeter range scale. Actually, ours is, if I remember right, it is like 4 mm by 4 mm. That is the diamond area of the device.
Okay, sir. Sir, 𝗕𝗫𝗙𝗪 is asking, how do material properties, band gap, defect density, surface area influence the sensitivity of metal oxide gas sensors?
Very good question, actually. So, see, as I told you in the beginning, there are kind of a different aspect coming from the electronic aspect, that is structural and electronic configuration aspect, which is playing a role, as well as the surface morphology. So, if you have a particular material, for example, N-type material, there is a kind of electron depletion layer will be formed. Okay, this depletion layer, which is playing important role in the sensing, this depletion layer depend on the material. So your material is having a good crystallinity or a very good required crystalline size or required grain boundaries. Everything is depending this depletion layers. Okay, that is the one concept that is playing a role in the response. So one has to tune to get a very good electron depletion layer that will respond. That is important for the response, gas response. And another one is the morphology. You can vary the surfaces morphology. So one way is varying the number surface. You can increase the amount of surface available for the gas interaction, as well as these surfaces are you are having a decorated particles or gold particles decorated. This will add to the electronic configuration also. So the depletion layer also defined by these surfaces, and surface energies are kind of I told you, like in these cases, because we are seeing only gas interaction. Okay, these cases we will be like we are not worried about the surface energy. It's a kind of a how how good the absorption energy is for the particular gas. That is what we are interested in. Surface energy playing a role. That's what I told you. All my theoretical calculation, we are calculating the absorption energies of the surface for the different gas molecules. So these absorption energies are playing a role in this. So you have to have a electronic configuration on the surface suitable for the gas and response, as well as the suitable absorption energies.
Okay. Okay, sir. Bijay Lakshmi is asking the upward and downward response, in bracket response and recovery of the same material with different types of target gas environments changes. Why?
I showed you, na. See, in the beginning slides, I have showed this one. If you see that this is coming from this concept, okay? When we have a N-type semiconductor or P-type semiconductor, okay, depending on type of this material, you have the resistance increase or decrease will happen for the reducing or oxidizing gas. If your gas is oxidizing gas, for the N-type material, the resistance increases. The same gas for the P-type material, the resistance decreases. Okay, that is mainly coming from how this depletion layer is interacting. Okay, the electron accumulation layer and the depletion layer. See, when you have that kind of oxidative gases, for example, the oxidative gases means like it will like kind of the take the electron from the accumulation layer. Okay, so when it takes the electron, okay, from this one, okay, so the electron configuration, that is the resistance of this material, will increase. That's why for the N-type material, the resistance increase. Similarly, for the P-type material, when you take the electron, in the P-type material, there is the whole conduction is happening. Okay, so due to that reason, whole conduction, when you take out the electron, the resistance will decrease because the whole conduction will increase. That's the reason resistance decreases. This is the explanation.
Okay, sir. Sir, again, Vijay Lakshmi is asking, gas sensor fabrication is available in your CNS Arkavati campus, Nelamangala, for other academic users?
Yes, ma'am. Actually, you may share my email ID. They can email me. It is available. Actually, we are having something called CRF, Central Research Facility. Okay, this Central Research Facility is one of the system where we allow both our user as well as the external users. Okay, so anybody has to register in the portal. Even my students, they want to use, they will register in the portal, and all the facilities available registered. Okay, they can choose, and for the external users, for the academic users, there will be nominal charges. Okay, so it is available, and if somebody wants to do in collaboration mode also, I look into it. But I'll be looking for something like which will be interesting to us, that is important to us, because our time and resources are very limited actually. Okay? So later contact me, I will talk to her.
Sir, again, Sankhamitra is asking, how does nanostructuring like nanowire, nanosheets improve gas absorption and sensor performance?
This is again like whatever I have showed you, I have told you, this is related to that only. See, this we can study with the different configurations actually, where people can take in 2D sheet or nanowires or something. The point is like you will have some different gas response. I'm not denying it, but the usual approach in this gas sensor field is like we will be seeing a reliable and kind of promising method for kind of scalable process. Okay, so like nanotubes also can be done. Actually, I have not done for this, but there are reports available. People take nanotubes and study. But the point is like, how do you further use these nanotubes and for the fabrication of gas sensor, like it is having more complication compared to our opinion. That's what we are not ventured no more into nanotubes. But there will be difference actually, because if you see the electric conductivity device, the 2D sheets and nanotubes and nanodots and nanoparticles, there will be a difference in conductivity. So as I told you, the electronic configuration playing a major role in this gas response. So accordingly, there will be a change in the gas response. There is no doubt about it. But you want to see that, like how you want to proceed with the study is important. Like you want to go for a large scale synthesis, doing application, then you have to take like with the method which will be giving a promising, the route which will be giving a promising material, which is scalable easily. But otherwise, you can use any material and each will have a different response studies. It is possible.
Yes, sir. So any other questions? Any other questions?
Yes, ma'am. Excuse me, sir. I have a question. Which type of sensor actually used to detect the gas?
Which type of sensor? I mean, which gas you want to detect?
Yes. No, sir.
No.
Which sensor? Means, is it catalytic?
Ma'am, actually, this is what I have been, I was presenting in this talk also. So, depending on the gases of interest, you have to choose a material. Okay.
Okay.
So, how this material interacting with the gases, you use to, well, like that will give you a change of resistance of this sensor, and then that will be used for measuring. I don't get your question fully. I'm sorry.
Sir, I want to know which sensor is used to detect the gas.
But all along the talk, I was talking about direction only, right?
Yes. No, sir. I want to know, is this a catalytic diffusion sensor?
Ma'am, actually, there is a catalytic effect as well. Actually, there are sensor, like catalytic effect is like we will improve the sensor response by catalytic effect by decorating these sensor surfaces we do. But essentially, this concept wise, like modifying that electronic like definition layers and the surfaces, that is what playing a major role.
Achha. Okay, sir.
Okay,
Thank
sir.
you, sir.
Okay, sir. There is another question. Which optimization strategy is most promising for room temperature, low power gas sensing?
Good question, actually. this Actually, this is very difficult to say that which strategy will be suitable for room temperature. But from my experience, I would say that for certain gases, room temperature sensing is possible. Room temperature sensing is possible for the certain gases. Okay, but for the some gases, this room temperature sensing is not very good actually. See, the problem with the room temperature sensing is your sensor has to respond to the gas, and when you remove the gas, the sensor too should relax to the original state. Okay, for certain gases, it is not possible. Okay, if you see our study, like our second study, NDNAO3 NIO, for the SO type of gases. In these sensors, okay, we have to have heating. Room temperature sensor, it will not work at all. The sensor will not come to the ground state. I mean, the original state when the gas is removed. So, room temperature is not possible at all. So, one has to use the heating. So, it depends on that. So, in my opinion, like for the SO2 kind of analysis which you are studied in this this SO2 gas, the heating is needed. Whereas in the case of CO or NO gases, room temperature is possible. Okay. And again, coming to the humidity is one of the important parameters. Okay. So because as I told you, the immunity layer, when you have more immunity, more hydrocarbons are going to form on your sensor surface. Okay, then accordingly the response is going to decrease. Okay, so we always do the kind of a controlled immunity study for these things. But when it comes to sensing platform, we have a immunity sensor installed in the sensor itself. So our data, we have the library data, which is where the response is collected at a different immunity level. So when you are doing a final machine learning programming, so this also will be one of the input. Okay, so the temperature is going to affect and the humidity is going to affect, and these two are fit to the programming, and the programming will take care of this. Even if it's humidity higher, also it will adjust accordingly. Okay, I hope I have answered this. Otherwise, like whether room temperature, the high temperature is always good. That's what I mentioned in the beginning itself. High temperature is always good for the gas sensor, but there is always debate. Like high sensor, high temperature means like more power is needed. That power also reduced. Okay, these are all the concept. Like we have to work with the basics of the material, like basic properties of material, as well as the final product requirements. Okay, that's how we optimize.
Okay, sir. So there is one last question. Is there any possibility to avoid the effect of relative humidity on the room temperature gas sensor?
No, ma'am. We cannot avoid actually. Okay, humidity part cannot be avoided. If you want to avoid, you can have the sensor kind of at higher temperature. See, that's what I told you. No, this is like if you are really interested in particular sensor, should particular gas, it has to show a very good response. Then one should go to sensor with the heating. So if you heat the sensor to above 100 degree, like about 120, 130, 140 around the temperature, then the sensor response will be very good. So with the heating, the response will be good. But again, like 120 degree heating, like you will be giving a high power. That is what the factor cost to. Otherwise, to avoid this humidity effect, the heating is the only way. Okay, but when you have the collection of sensors, we have to have a standard humidity sensor and kind of nullify this effect. That's how one has to do by using a program. Otherwise, in the sensor, the response, if there is a humidity, accordingly, your response will be changing. It cannot be avoided. Room temperature, you cannot avoid the humidity effect.
Okay, sir. So any other questions, participants? Okay. Thank you so much, sir. Thank you so much for having us. Thank you so much.
But again, actually, I am like happy to see like about 120 people are attending the talk at these hours. Actually, is really good to see. Okay, keep it up. Okay.
Thank you, sir. Thank
I
you
don't know.
so much, sir.
I will be eligible to wish you people like you maybe elder than me. So I can say that good luck to all of you.
Thank you so much, sir.
Nice to.
Thank you so much.
Thank you,
sir. Sir, you may stop sharing.
Yeah, thank you. I don't know. I will. Yeah. Okay, it's there. Okay. May I leave?
Yes, sir. Yes, sir. You may.
Thank you very much.
Thank you, sir. Okay. Thank you so much, dear participants. So with this, we are concluding our third day of FSFM 2025. Now kindly join by 6 p.m. tomorrow for some wonderful sessions by Dr. Sarath Kumar Maharana and 𝗕𝗏 𝗙𝗏 sir. And lastly, I want to clarify something regarding attendance. Please note that no Google form will be provided from today onwards. We will extract the participants list from Zoom and take attendance accordingly. So thank you so much for your considerations. Thank you and good night.